Okay, welcome back to the post-lunch session, and we have again, a series of exciting talks. First, to start with Priya Hasan. Priya, your talk is. Hi, Priya. Can you hear us?
Yeah, I can hear you.
Yeah. So your talk is for 15 minutes. So maybe 13 plus 2.
Yeah.
And we'll give you indication 10 minutes. After 10 minutes, I'll give you an indication that you have 3 minutes left.
Okay. Okay. Thanks, Somav. Thank you.
Well, the floor is yours.
Thank you. Yeah. So hello everyone, and thank you for giving me this opportunity to present work done by one of our students, and which we've been doing it. So basically, this is about the effect of gas content on galactic disk thickness as well as star formation activities due to minor mergers. Okay, this is a hydrodynamical study, and this has been done PhD work, which has been done with our student Shweta Kalakapalli and SN Hasan. So we've been working together on this problem. And yeah, so just as this thing, introduction to minor mergers. I'm sure people are familiar with that. I'll talk about the simulation methodology we've used. Then our key result, one about gas driving star formation, and the other one about gas protecting the thickness in a way. And then we talk about the role of gas, implications for galaxy evolution, and then conclusions. So let's start off with what exactly are minor mergers. Minor mergers are mergers which are with mass ratios 1:10 or 1:100, where the primary galaxy is much larger than the secondary. And these we've realized that these are very important ones because in principle they are at least 10 times more frequent than major mergers. And these are the ones which should be contributing to this formation. And like we'll show in this, it would also trigger star formation, build stellar halos. And it actually tells us about how do thin disks, for example, in the end, we'd be talking about Milky Way. And we would like to also know how do thin disks like the Milky Ways actually survive when you have so many frequent minor mergers. So the tool we've used in this is the thing called Gadget. I'm sure many of you are familiar with it. And then I saw there's a hands-on session on it. So Gadget is a hydrodynamical simulation code for galaxy mergers. It is the very code that has been used for the Millennium Run, showing for galaxy formation simulations, for dark matter structure, and various other things. So this is the Gadget code which we basically used for this work. So so what were the parameters? What we used is we used a mass ratio 1:10, and the primary disk mass was about 4 × 10^10. Secondary distance was about 100 kiloparsecs, redshift range 1 to 0. We started off some time back, so we started off with Gadget 2 and moved towards Gadget 4. And we've also been using DICE to get the initial parameters. The gas fraction, we have varied it from 0 to 40% for our models. And so the galaxy models, what we basically used was the dark matter profile was taken the NFW1, the stellar disk was taken to be exponential, the gaseous disk also to be exponential, while the bulge was the Hörnquist model. So the first result which we got when we actually ran this thing, sorry, I've not mentioned over here, but we actually used a computer, there is a IIIT here in Hyderabad, which has a cluster, and we basically use those computers for our simulation work. And the first result that we got for our simulations, which we got, was that we saw that obviously, like we expect, that the more gas you have, the obviously more star formation you have. It's a clear monotonic relationship. So if you can actually see that as we increase the initial mass, the mass of the initial gas, you see the number of new stars increasing to a large extent. So for example, for 40%, we have 56.8% conversion. And with 10% we have this, which is kind of what is expected, that you would expect that with the increase in the gas content, you would obviously have a larger star formation thing taking place. Okay. So if we visualize it also, what is interesting is that, I'm sure, this image is not too great, but you can see that here I have for different gas ratios, you can see the number of new particles which are formed in each simulation, like I said, which increased with time. And what you can typically see is that in this one, the central graph what you have is you can actually see the older stellar population. This is as it was before the merger. But now what you see after the merger takes place, you can see that the stars they seem to settle down in the disk. So actually what we see is that there is an increase obviously in the disk thickness, right? But you can see that it changes with increase in mass, which will actually come in the next result, which is about the disk thickness. So what we found in the disk thickness is that obviously with the merger, you do have an increase in the thickness, but the increase in this thickness, it decreases with the increase of gas content. Okay, so it's as though as the gas percentage increases, the increase in thickness keeps decreasing. Okay, so typically if you had 0% gas added in, you would have a largest increase in the thickness. But if you have a larger amount of gas, you basically have a thinner disk, okay, compared to the one with the lesser gas content. So it is the smallest when your gas content is the largest. Now this was an interesting thing. So this graph doesn't show it too well, but it actually shows you that if you pre-merger you had a thin distribution, which is the dashed line, the yellow one, then that you see that as you increase the gas content, it becomes thinner, okay, with the increasing gas content. And therefore we propose that probably the gas actually has some kind of a protection mechanism, in the sense that obviously when you start off with the merger, the satellite obviously perturbs the disk and you have kinetic energy being transformed, but then the gas absorbs the energy like the stars do, and but it kind of more of the stars do not end up with so much of heating, in the sense they don't thicken the disk so much, because the stars actually radiate most of the heat, and they end up becoming lying in the thinner final disk, the stars, and therefore in a way the gas actually behaves like some kind of a shock absorber. So if you start off with your merger, like I said earlier, if you have more gas content, you'll have the stars sitting onto a thinner disk compared to what you're this thing. So the gas actually behaves like some kind of a shock absorber. It's kind of this thing. So actually gas plays a dual role. If you see what is gas actually doing, is that obviously in terms of star formation, more gas you have more stars, and the mechanism is through compression, which triggers the collapse. But it also behaves like some kind of a protector, where if you have more gas, you'll have lesser thickening. Okay. And this the mechanism which is doing this is basically energy absorption and dissipation, due to which the disk gets kind of thinner. Yeah. So this is actually it's kind of a paradox, because you'd basically say that your gas-rich mergers, if they are gas-rich, they produce more stars and less overall thickening. And like we said, basically because the new stars are formed from the processed gas, and the energy absorption happens before the stars form. And therefore, all stars are protected kind of from full heating, while the new stars settle in an already stabilized disk. Now, this kind of does agree with some of the results which are there from literature, from papers by Moster et al. As well as Q et al. And then what you can actually see, what is the implications for the Milky Way. So you see that the thin disk scale height is about 300 to 400 parsecs, while the thick disk scale height is about 1 to 1.5 kiloparsec. And if you look at the gas fraction, it's about 20%. So actually for the Milky Way, we are kind of in between. We are not at the low gas value and neither are we at the high gas value. We are something in between. So therefore, separating this is kind of a little complicated. So like we said, 20% gas, which is there in the Milky Way, it does provide sufficient protection. It explains thin disk survival post mergers, because you basically this thing, and it's consistent with the Sagittarius dwarf tidal stream evidence. So actually, if we look at galaxy population predictions in high redshift galaxies, which have a high gas content, say 40 to 60%, then in that case, the outcome of the merger would imply minimum thickening with intense starburst. Star-forming spirals, these have typically 20 to 30% of gas, And therefore, for these, you would have moderate thickening, enhanced star formation. Early type SO galaxies, you have lesser gas content, less than 10%. So you'd have significant thickening and low star formation. And then I think the biggest issue lies with the dwarfs, because for dwarfs, since the gas content is variable, it is very difficult to actually state what would actually be the merger the merger outcome, because the gas content of dwarf galaxies is actually variable. So minor mergers actually have observational signatures like stellar excess at large scale heights and radial scale lengths, thin component, rotational lag, etc. And so the summary of the key results which I told you is that star formation, 37 to 50% of the gas converts to stars during 1:10 mergers. So basically you do have enhanced star formation, that's for sure. But the gas fraction would actually define how much of thickness do you get for the disk. Because of the gas absorbs kinetic energy that would otherwise heat the stars. New stars form the processed gas and therefore they settle in the disk without major thickening. And this kind of explains why do you have thin disk survival in the Milky Way. The limitations obviously in this study are we are looking at idealized single mergers, not full merger histories, with fixed orbital parameters and a simplified star formation feedback, limited resolution, etc. And we've only taken a 1:10 ratio. So the future directions is basically obviously looking at cosmological simulations, etc. And what we are even more interested on is applying it for the Milky Way. Specifically now, because with Gaia data, we have a very clear merger history of the Milky Way. And then with this merger of history of the Milky Way, we would like to actually study how do you actually build up the thin disk and the thick disk, etc. As well as we are actually, work is ongoing. We are trying to fit the star formation bumps, the peaks that we are getting in star formation with the merger history, with the kind of values, if they can match with, the gas content values, etc., depending upon the star formation history we are getting with the merger history of the Milky Way. So this is an ongoing work, and we hope to now extend it well to the Milky Way, since now our simulations has done, and now we would like to correlate this with observational data from Gaia. So I'll end with that and be happy to take questions.
Okay, thanks, Priya.
Yeah.
I get some questions. Like to hear first from the RD failure side. They like this.
Okay.
Yes.
I have a question. Maybe you can tell what was used all this is.
Can you be a little louder? I somehow can't hear well.
I'll tell you the question.
Yes. What was it gadget? What was used to evolve the system?
Okay, so there is a question from Aushavi, and she was asking, like, what board you used? Is it gadget or some other?
Gadget with that. Yeah.
Okay, there's another question from Sandeep Kataria, and he was asking, like, what is the exact mechanism that if you increase the gas fraction, that sort of increases the thickness of the disk? Yes.
So actually, that's what I found, that from the simulations, we found a reverse kind of a thing. That means if you have a larger gas content, your disk gets thinner, right? That was what we found. That was what we got from the simulations. So like we said, it's in a way that, the stars, the gas absorbs the energy and the stars somehow land in the thinner disk. That's what we got in the simulations, which, like I said, is what we're using to explain the thin disk survival of the Milky Way with this thing.
Is there any other questions? If not, then I'd like to ask one question. So in your star formation recipe, what was the threshold used? Is it the density, like critical density, or is like you transform the gas to stars, or also like there's a threshold temperature?
I think it's critical density. Actually, the student was running the simulation, so I'm not very sure. But I think it is critical density. I'm not too sure. I think so.
And did you also play it around with the star formation efficiency? Because like even if you have 10% gas, if your star formation efficiency is more, then you can convert like, more gas into stars.
Yeah, no, we kept that constant. We kept that constant. Because we didn't want to change too many parameters, otherwise it will make it more. So yeah, we kept that constant. Yeah, thanks.
Is there any other question? If not, let's thank Priya once again for her wonderful talk. Why is the guy who is? That's fine. So our next speaker is Subhrata Dey.
Hello.
Yes. Can you please share your slide?
Yeah, but it's saying sharing is not turned on yet.
Okay. I can send us a request. Can you try now?
Yeah. No request. Wait 1 second. Still saying sharing is not turned. Okay. Now it's fine. Thanks. Just give me
It's been enabled. You can try now.
Yes. I think it is working. Just give me a minute. Can you see my screen?
Give it a moment. Yes. Can you make it full screen?
Yes. Yeah. It's visible, right?
Yes.
Yeah, perfect.
Okay, perfect. So, yeah.
Just a moment. We're just fixing some technical issues. We can make it full screen here as well. Yes. Okay, perfect. So the talk is for 15 minutes, so 30 plus 2. So I'll give you like an indicator that you have 3 minutes left. Okay?
Sure.
So
Sure.
you may speak.
Okay. Hello, everyone. I'm Subhrata Dey. I'm a postdoc at the National Center for Nuclear Research in Warsaw, in Poland, and I'll be talking to you about deep learning approaches to galaxy merger identification and classification, which I'm doing with William Pearson and our student, PhD student, Aidan Cotter. So before I begin, I would really like to show this image, and I hope it was shown before. This is the first light image of the LSST, and besides, I mean, you can clearly see that the star of this image is the merger galaxy that you see here on the top. So beside all the scientific importance that these merger galaxies have, it's also shows us the beauty of being alive in these times where we can see the cosmos at such extraordinary details. So to start with, why galaxy mergers are important. So galaxy mergers basically shapes the galaxy. They alter the structure, dynamics, and size of the galaxy. They trigger star formation, as we heard from Priya's talk, that the interaction compresses gas clouds, triggers bursts of star formation. They also fuel the activity of AGN, that is merger channels gas to the galaxy center, and then it fuels the AGN activity. And it also redistributes the material. So when mergers are happening, the stars, gas, metals gets mixed up and spread across the galaxy. Further, in the cosmic scale, when we zoom out, the mergers are very important for galaxy growth. So the hierarchical merging is a key path for building massive galaxy. And also, merger traces the cosmic evolution. That is, the merger rate traces how exactly reflects how the structure formation progress across the cosmic time. So, needless to say, merger are fundamental driver of galaxy evolution. Now, for us to study the mergers, it's very important to identify the mergers. So one of the oldest method is visually classifying. Okay, you have two images. You go through the images and you see, okay, this looks like a non-merger spiral galaxy. So this might be non-merger, and then these are probably merger galaxies. But then you have images like this, which are very high redshift galaxies, and it's very difficult to understand what exactly is a merger, right? Here you can see that the significant features of merger galaxies, such as the tidal tails or plumes or double nuclei, none of those are very clearly visible. Also, if we consider ourselves human as resources, then visual classification is very resource intensive. So very difficult to do a large data classification by just by us classifying visually, right? Further, another merger identification is the close pair method. That is, you have galaxies in the sky projected at some distance. We measure the redshift or the velocity, and then we see how nearby they are. So, if the galaxies are close to on the sky by 20 to 50 kiloparsec, we say that okay, these are potential merger candidates. Now, the drawback of this is first, we need a lot of spectroscopy here. So, and we know that spectroscopy is very heavy, like very difficult to get now. And also that these
sorry to interrupt here. So here on our like Zoom screen and all this, yeah. So there's a significant lag between like you changing the slide and what
I see.
Yeah. So we miss sort of like, yeah, so visual
Could you
classification.
maybe point the camera to the screen? Then I will be maybe aware of how exactly, because I can just see half of the screen, not the complete screen.
Just not this. The shooting camera is not.
Wait. I can see the IIA camera and it is just, I'm just seeing the speaker podium, not the screen. Yeah. Yeah, a bit more towards the right.
Is it okay
A little bit more, sorry. Yeah, this is good enough. I can trace it. Okay.
Yeah, please go.
Okay. So, as I was saying, visual classification is very resource intensive. So, okay, there is a lag. It's not going to the next screen. It's still stuck at the same screen, right?
Yes.
Oh, maybe I'll try to download it as a PDF and then show you that. Just give me 1 second. I'll just quickly download it. Can you see this now? Okay. I think this is better. Okay, perfect. Okay, perfect. So, yeah. So as I was saying, so this is the close pair method that is like you have some projected galaxy on the sky. You need the spectroscopy to understand the redshift, and then or the distance between them. We say that if they're less than 20 to 50 kiloparsec, okay, these are potential candidate of merger. But the problem with this method is we only identify the pre-merger galaxies, not the post-merger or merging galaxies. So there is one drawback with the close pair method. And also, as we know, getting spectroscopy of galaxies is quite intense, like difficult. So yeah, so close pair indeed becomes difficult to identify merger galaxies. Further, another interesting way to understand galaxies, identify merger galaxies are morphological cuts. So you have the galaxy, you understand you get some morphological parameters, you put it into the space of morphological parameters, and then you see how they're behaving. So are they preferring certain type of morphological parameters? Mergers are preferring certain types of morphological parameters compared to non-morphological parameters, non-merge non-mergers, sorry. So with respect to morphological parameters, there are certain systems like CAS, that is concentration, asymmetry, and smoothness. So concentration basically tells us is the ratio between the radii including 20% to the 80% of the light. Then we have asymmetry, which basically we take the image, we rotate the image, and then we subtract the pixel, and then we sum it. So that is the asymmetry. And then we have the smoothness, which is similar to asymmetry. We just take the image, we smooth the image, then we subtract from the original, and then we sum the pixels. Further, we also have something called Gini M20. So Gini is basically tells us it's borrowed from econometric statistics. So it was used to understand what is the distribution of wealth between the rich and the poor. So amazing, we are applying on astronomy now. So Ginny tells us describes the inequality in the pixel brightness. So if the light is concentrated in particular pixels or they are well distributed. So Gini 0 is like, okay, the pixels, the light is well distributed, or Gini 1 is like, okay, it's concentrated at certain pixels only. And then we have the M20. It's basically this, it's a quite complicated term called the second order moment of the brightness 20. So basically it traces the distribution of the bright structures, as you can see here in the screen. So from low to high, it tells us how the brightness of the source structure, bright structures are distributed in the galaxy. So in the past, Gini M20 has been quite exhaustively used to answers to classify the merger non-merger. So this is a study by Rodriguez Gomez, which used the very famous cut by the Lords et al. 2008. So on the screen, what you see on the top are the mergers, and the bottom, and then there is a cut, and here what you see is the non-merger. Now this study is a bit biased because then in 2008 the mergers were only classified as the infrared bright galaxies. So they did not consider the other mergers which had low infrared low infrared luminosity, but were still merging system. So they were also missing low mass galaxies. So this was updated by Aidan, our PhD student. So he used illustrious TNG simulation data, which I'll be talking very soon about. So use those cut where we had simulations of merging galaxies, and then we tried to study the morphology, how these galaxies are behaving. So these statistics, the morphological cuts were updated, as you can see from here to here, with the MCMC criteria applied. So my major work here is using now deep learning, that is machine learning methods, to understand how galaxy mergers, how to identify galaxy mergers and also classify. So as we know, machine learning is a very powerful approach to automatically classify galaxy merger from imaging data. So it basically learns from pattern and makes ideal for complex tasks like galaxy classification. It's basically a black box, which is kind of doing series of matrix multiplication, as I would like to say. So till now, whatever methods I discussed were majorly focused on classifying between merger and non-merger classification. And my aim is to go beyond the merger non-merger classification to sequence it to merger history like non-merger, pre-merger, ongoing merger, and post-merger galaxies. Further, one of the another main goal is to create a science-ready catalog. So this is for the not ecliptic pole of the galaxy. So William Pearson, with whom I'm working, he already created a merger non-merger catalog for this not ecliptic pole area of the sky, which is like 5.4 degrees square. It is a plethora of multiwavelength data, so a lot of potential science to do. And it is also a subfield of Euclid. So that is quite amazing as well. So my aim is to extend this work by creating a comprehensive catalog for the not ecliptic field which includes the non-merger, pre-merger, ongoing merger, and the post-merger galaxies. So this is kind of the workflow of the merger classification, that we acquire the mock images from the HSC, we data process, we apply merger deep learning classification, we classify the merger states, and then we analyze it. So for our data, me and Aidan, both of us were using data from this famous galaxy merger, the merger challenge, which was led by Berta Marglev Bentabol from Schroen, Kaptein Institute, Netherlands. And what they did was they had illustrious TNG images. Sorry, I think I missed it. Anyways, so mock HSC images, so illustrious TNG images, which are mocked for HSC type HSC observations. And with that, they asked bunch of machine learners, experts, to classify the galaxies basically into merger, non-merger, non-merger, pre-merger, post-merger, and ongoing merger. So you can see here on your screen there are different merger, the machine learning algorithms that were used by different experts to classify these galaxies. So random forest, swine, zoobot, and 3 CNN type networks. So what I did was I took the same images And then I applied data processing. So what machine learning does is, if you give it a same image and you data process it, for example, you crop it or you rotate it, it sees it as a different image. So it's a second image. So that helps us to increase the number of galaxies that the networks are seeing. So my data processing basically includes the original image, which I rotated. So that increased the number of galaxies. Then I flipped. I cropped it with 100 kiloparsec, and I also scaled the images by arc-Sinet scaling to enhance the faint features of the merging galaxies, such as the tidal, double nuclei, etc. And with that, I applied a deep learning classification. I used basically 5 networks, as you can see here, the ZooBot convex net. So ZooBot is efficient net, rest net, swine transformer, and vision transformer. So my main aim to use all of these rather than just going with one network was to focus on was to capture the diverse morphological parameters that the networks might focus on. So, okay, thank you. So, for example, one particular network might focus on one particular type of morphology only. So, the whole point of using the diverse network system is to kind of get an overall estimation of how classifications are done. So, this is the ensemble method. And with this, we combine prediction from all the method, and the final class, the final prediction of the image was chosen when we have a confidence greater than 0.7 probability. So my networks are predicting, are learning from the images. Then we are creating a test sample, and it is predicting on the test sample. So if the test images, if the confidence is greater than 0.7 for any of the networks, we consider it as a true label for the images. So this is the classifier performance, as you can see. So when we have this, there are 3 matrices through which we can classify the performance: the accuracy, which defines overall correctness of the model, so how well the correct predictions are. Then we have precision, so how precisely is measuring how reliable the positive predictions it is giving are. And then we have something called recall, so it tells us how complete the model identifies the positive. So here you can see all the networks that I used, and here are the statistics that you see, the precision, recall, and then the ensemble method. That is when we combine all the information from all the networks, and then we see how the performance is. Ensemble is behaving fantastic, so which is quite convincing for us. So this is kind of giving you a more detailed perspective. So we had the architecture, so different ensemble, ZooBot, VIT, etc. And then we are having the classification here. So here in the color bar, you see the precision. So the darker the image, the precisely it could determine the stage of the merger. And then the numbers are the recall. So how complete the identification was. So as you can see, ensemble again behaved better in all terms compared to all of the other networks that we have. And then, okay, with the ensemble prediction, now we were trying to see how, with respect to different properties such as redshift or mass, these statistics are behaving. So what we see here is non-merger precision is more or less same, but the recall shows a very interesting distinction. So we see that for the recall, ongoing and post-mergers are kind of struggling compared to non-mergers and pre-merger. So it is quite true, because post-mergers have very faint features, and it becomes difficult sometimes for network to detect those faint features. So hence it is kind of not performing as well as the others. And then we also compared the performance with respect to mass. So we can go from recall and then look at the precision. So you see here, the blue is the non-merger, the orange is the pre-merger, and then we have the post-merger in the red and ongoing in the green. So you can see here that the non-mergers, until some stellar mass behaves fantastic, and then there's a sudden drop. And exactly at those points, we see an increase in the post-merger and ongoing merger. So non-merger, so high mass non-mergers show some more morphological disturbance. So our networks are classifying them as post-mergers compared to non-mergers. And then when we see the precision, there is therefore an increase in the precise detection of non-mergers compared to the pre-merger, ongoing merger, and then the post-merger. So then I will just leave you with the summary and outlook. So this is work in progress. We are still working on it. The main aim of this is to apply on real HSC data. So we are fine tuning our network so that we can further apply on real data. So thank you. I cannot hear you. Sorry. Hello. I think you're muted. I cannot hear you.
Can you hear us now?
Yes, yes. Thank you. Yes.
Yeah. So due to our poor Wi-Fi, the last 1 minute we actually dropped out. So
Okay.
think the last slide, maybe the summary of the future.
Okay. So you can see this last slide, right? Okay, so well, the main summary to the takeaway message is besides focusing on single network, it's better to consider ensemble network, which as we saw, it gave the best performance, and also it kind of focuses on variety of the morphology and captures it well and has a much better classification than the single network dependent. And we also saw that the network show a high dependence on mass, which is quite interesting, with performance varying significantly across mass range. And as respect to the future outlook, so our main aim is to build a non-merger, pre-merger, ongoing, and post-merger catalog for the not ecliptic pole region of the sky for the HSC data. And this will definitely, these architectures will definitely be transferred to LSST and Euclid, considering its depth and sensitivity. So this is the work in progress, as I would like to say. Yeah, thank you.
Thanks. Time for a quick 1 or 2 questions. Yes, please.
Yeah. So in you have mentioned of the architectures like Zubot and all. So there is a one architecture AlexNet. People use it for classify the galaxy images. It is not in your architecture. Is there any reason?
No, so I did not use AlexNet, but I think ResNet are kind of FNet, ResNet are updated version of AlexNet. So they are kind of evolving the same AlexNet into a much more complex networks. So yeah, that's what I did not use AlexNet, but I think ResNet and FNets are more updated networks compared to AlexNet.
Yes, please.
You can repeat that. So, let's say to go to sample size of the box and how that depends on the different network that.
So there's one question from Sudhanshu Barman. He was just asking, what is the sample size for your mock images that you use for this exercise?
Very dependent on 5 networks.
And does it have any dependence on the 5 network or architectures you use for this?
So I am using around 10 power 5 images total. So I think that's a good amount. And but for each class, basically. So for each class, I have a merger, non-merger, pre-merger, and post-merger. I have 10 per 5 images for each classes. And the second question was, does it have any, does the architecture have any dependence on the morphology?
The sample size.
I'm sorry?
Sample size.
Size. Well, I did not.
The performance of your,
I did not see any such dependence.
Sorry, can you hear us?
Hello? Yes, I think. I did not see any dependence, to be honest. So, hello.
Is there any other question from the audience? Any other question? If not, let's thank her once again.
Thank you.
Share the screen. Here we have to put the, here is this, speaker is Saili from IIA. So,
Hello everyone, I'm a PhD student here at IIA. So today morning we had very nice introduction on the Galaxy Bulges. So galaxy mergers are basically classified based upon the galaxies that are being merged, and another classification is upon the gas richness of the galaxies that are being merged. So now based upon the mass of the galaxy that are being merged, there are two types of galaxy merger. It's not coming here. So major merger and minor merger. So if the two galaxies that are being merged, the mass ratio is 0.7 to 1, then it is called like it's come under the major merger classification. And the process is very catastrophic. So you start like expect we have a very like the different picture that we have like after post merger the structure that we see, it can last for a few bigger years. Whereas in the minor merger, the two galaxies that are being merged are having the mass ratio less than 0.7, and this process is not as much as like catastrophic compared to the major merger, but you can see still the order is and the structure that are being associated, the lifetime is around 1 to 2 gigayear or even shorter. And based upon the gas richness, the two galaxies that are being merged, whether they have lots of gas, so it's called wet merger, and if they don't have gas, it is called dry merger. So in the process of dry merger, you won't see star formation, but the overall mass of the post-merger galaxy will rise. Whereas in the wet merger, the two galaxies that are being merged, it triggered a lot of star formation because of the presence of gas. So this is an example of again from Galaxy simulation. This paper has reported. So where two galaxies you can see are being merged. So this is a small galaxy and the larger galaxy. So small galaxy is being created in this galaxy. Now you can see it has a spiral late time galaxy, and like the time scale also being shown how the galaxy merger is being happened. And at the later stage, when the whole like two galaxies have been merged, you can see the post merger stage, but there are lots of deeper kind of structure that we call shell, which is being like appearing after the merger has been completed. So in a recent work by Giri et al. Okay. There are some images, but it's not coming here.
Yes.
One more time, you press. No, it's a single slide.
Okay. You are better.
Yeah. So there are recent paper by Giri et al. And they have identified 11 such merger element feature. So if you see in this example, like images, this first galaxy is having lots of ripple tail structures, whereas in the middle galaxy is a tadpole galaxy, which is long tidal tail structure, and the third galaxy has a very like wrapped disk kind of structure, which is the central dust displacement. So all these structures you can identify from the optical image of the galaxy also. So yeah, so in optical image, you can perform some imaging technique, like you can model the smooth line, remove the smooth line, and in the visible image, you can see some structure. So here is the optical like argon image of the galaxy, and when you model and then remove the light, you will see some central structure like the ring kind of structures around. While in this process, you can see some disturbed structure, while the second galaxy in the bottom, you can see some X kind of structure. So these structures are basically appearing when you do some modeling on the optical image of the galaxy, and the residual image you can see that okay, yeah, this galaxy has some residual structure, that means some merger activity has happened, and already this galaxy has been classified as an early time galaxy. This is not associated with any late time structures. So these are some other structures also, like you see in this example, the isopores central like the white curtains are changing the position angle, which is called the isopore twisting. Whereas here in the top image, the galaxy has showing kind of disky kind of isopods, while it is showing the boxy isopod. So these are like different type of merger element that we see in the early type galaxies. So I'll just show one movie. Yeah. So here, this is one galaxy I am going to talk about here. So you see there are two galaxies that are being merged. So the smaller galaxy are passing through the bigger galaxy center, pericentric passage that we call. And after like 5 to 6 pericentric passes, the two galaxies are being completely merged, and we see the ripple kind of structure that are being propagated in the outskirts. So and the cell kind of structure is being formed. So this galaxy is basically a very famous galaxy simulation. That galaxy is called ABC 4993, which is a galaxy that is the site of gravitational wave host, where the electromagnetic counterpart has been observed. So this is a basically gravitational wave was created by the binary neutron star merger. And if you see the electromagnetic counterpart was being observed from here, which is a short GRT. And after like how with time it's been fading. So the event has happened on 17th August 2017, and on like here the zip file is showing that at August 20 it's been faded. So my interest is not on the transient object but on the host galaxy. Okay, so NGC 4993 is this is the image in the at the right corner. If you see the galaxy, it's a featureless galaxy, has lots of shells features, but the center is completely smooth. So it's an S0 galaxy. And the zoomed in version, if you see, it has lots of dust layer associated in the image. So this is the HST606 optical image, which traces lots of dust feature in terms of spiral structure. So this galaxy has been modeled using Sarsic profile Sarsic for bulge and disk. And they have found it's a mostly bulge dominated galaxy with higher Sarsic index. Its stellar mass is of the order of 10 to the power like 11 solar mass, and most of the population of this galaxy is older population. So they don't have any younger population. So it's like mostly 3 gigayear or above. And this study also have reported that the galaxy have undergone a recent merger within the like time scale of 1 gigayear. Okay, so the simulation that I have shown was used gadget, and they have basically created the simulated image of the galaxy. So in the left here, this is the simulated image of the galaxy, and here is the HST image of the galaxy. And if you see, they look more or less same, except for the bright star that are being that are present in the observed image, which is absent here. So what is the mechanism here? So you model the galaxy using some model, like for example, they are using ellipse fitting model or Sarsic profile like using the galaxy. And then you remove that model from the observed image, you will get the residual image. So in the residual image, what you will see that they are saying the residual is contribution of the secondary galaxies that are being accreted. So from the simulated galaxy, they have basically created the model, and then they have subtracted the model and got the residual image. They have masked the central region because the central region is dominated by the dust. So if you like want to calculate the light from the galaxy and then dust contribution will be there, so that will basically bias your measurements. So that's why they have masked the central region, and then the rest of the part they have calculated the surface brightness. They have like got the surface brightness from the model, and then they have taken the ratio. From the ratio, from the surface brightness ratio, they have converted into mass, and they have got some mass for the simulated galaxy. The same procedure they have applied on the observed galaxy, the HST. Yeah, using different mechanisms like using ellipse fitting, where the center is being fixed. Second process is ellipse fitting they are using, but the center is not fixed. Ellipticity and position angle are also vary. And similarly, third process, they have used different sigma clipping method. And the fourth is this, they have used the Galactic modeling, and then they have like single Sarsic fitting, and then they got the corresponding residual. So what they found in the from the simulation mass estimation and from the observed galaxy mass estimation, the mass estimated from the observed galaxy is 2 to 3 times higher. So in the initial simulation, they have assumed the mass ratio is 0.1 for between the smaller galaxy and the larger galaxy. But in the when they are calculating the mass, estimating the mass from the observations, they're finding they're getting is 2 to 3 times of the larger than the simulation masses. It's mostly 0.2 to 0.3 times is the ratio between the two galaxy masses, which is again in the minor merger category. So interesting part of this galaxy is, so this is the galaxy, the gravitational wave that SGRT is observed from here. This is the central region where the dust lanes are showing in the optical image. Here, the contours are taken from the nitrogen line, N2 line. So if you see in the N2 line contour, you can see some spiral features along with the central bar structure. But in this galaxy, there is no bar in the stellar line. But the gas shows some bar kind of structure, which is the presence of a gas bar. Now, what could be the this bar? So we looked into their detailed kinematics, and we found that so this is the HST image, and this is the MUSE field of the galaxy, which covers the central region. Of course, not the shell part. And then we extracted their kinematics. So stellar kinematics shows nice rotation. The galaxy is having very nice rotation, like disk rotation. Whereas in the H alpha velocity, we found it has some decoupled H alpha rotation in the galaxy, which is not following the same which is following the spiral pattern that we saw in the N2 emission as well. So what could be this H alpha emission? Whether this is associated with some star formation or some soft excitation due to the high ionization kind of emissions. So to do that, we looked into its PVD characteristic, and we found that it shows some liner type of emission, extended emission. But again, we can't say it as an extended emission emission because it's very symmetric on either side of the center nuclei. So we did another like whether it's the actual liner type of emission or layer kind of emission. That's when we plotted band diagram, and we found that it's actually not extended emission, extended nuclear emission. Nucleus is there in the center, but the extended emission is kind of RG type of emission, which is retired galaxy emission, which is mostly coming from the post-HEP population. So yeah, so there is a population of stars which is a 1 to 2 giga-year-old, not young population, not any age emission also. So now, what is causing the existence of this gas bar? So this is again, what we did, we took the J-band image, we modeled the ellipse, or we performed the ellipse modeling task, and then we removed the model and took out the residual. So here, this is the entire frame residual, and this is the zoomed in version of the central region. And this, the sharp contours are taken from the N2 lines, and then we see that the bar region has some stellar light presence on the J band, which is again older population that is there. So this, if it is what can be the origin behind this kind of gas? So there could be two possibilities. The galaxy that has been accreted is a late type bar spiral galaxy which still holds its bar. So this is a pre-existing bar, and this can be found in the galaxies that are being merged having masses of 1.1:5. So this could be one of the scenario where the galaxy is accreting and having late type bar. The bar is still existing where the galaxies the spiral features are being destroyed. And other scenario is the transient bar. So due to the disturbed potential, the bar is being formed, like the tidal bar structure is being formed, which can last few million years. So we are not sure yet how this gas bar that is existing, and which is situated or overlying with the residual image center structure. And this gas bar has size of 0.5 kpc, and we have to find out in this sense, in the stellar structure, if the bar is still there, what is its size and how the stellar structure and the gas bar structure that we are seeing are varying. Yeah, I'm done. So this is an open thing. There are many people who work on bar, so I want some feedback on that, and it will help to conclude this work also. Yeah, with this I'd like to finish. So, there is no confusion there.
Time for questions.
Just wondering how does the active reality of some people from the agriculture?
Okay, I have plotted the gas phase metallicity, oxygen abundances, but it is not here right now. Maybe I can show you that. No, I don't remember the numbers. Yeah, I haven't looked into. I have those that I can just show.
Any other question?
What is the size in the plastic of the small gas bar?
In 0.5. So that I just roughly did from this ellipse fitting on the image. It's 0.5 kpc. Yeah. So from the higher, from the maximum electricity, I got
You think it could be actually a squiggle instead of a bar?
It can be, but because I haven't performed the Galactic modeling, so they have just used one single surgic to fit the bulge. I can use one more exponential or surgic profile and can see whether it's a bulge. But the gas bar is very nicely visible. The structure.
What you see is basically a oval structure, but the beauty is to it is the bar.
Yeah.
I don't see the position angle is quite constant within the bar.
Yeah, but electricity you can't again. It's almost going 0.5. It's not that small. It's going.
If you have bar there, of course your position angle will not
change much.
Here it's
But if you see, it's not changing much. In this region, it is almost few 5 degree or so, not changing much. This is -20. 5 to 10 degree, you can expect the change in the position angle also while calibrating the part.
So, any other questions? Please.
Yeah, so that's the question, whether the pre-existing bar is still holding on there. or the merger is inducing the formation of a transient part. So that's the question. Like,
The merger time
yeah. So this is like whether anyone has worked on the merge after like merger, how the galaxy is being evolved. Like once the merger has happened, because the population that I had showed, they're stopping when the merger has happened, the cells are being formed. But afterwards, I don't know like how long they can sustain. Yeah, the signatures, I have the O3 emission images, is there. But H alpha, what happens? So if you see these circles are from N to gas cycle, not from the H alpha. Because in H alpha, I don't see the emissions along the bar at the end of the, like the bar that I am calling as a bar, is there present at the end of the bar, not throughout the bar. O3 is also showing the similar nature. That's why it is mostly dominated into a N2 emission. That's why in the, like if you see the PPT diagnostic, it is coming as linear because it is mostly the N2 is dominating, that's why it is shifting towards the rightwards.
Don't you think it could be output?
No, it could be output. That's why we looked at the Venn diagram because extended line and emissions is there. But in Venn diagram, it is coming as a retired, like post HTTP
You look at the gas panel.
I do have gas panel. I have the H alpha only, but I have other lines.
One question each. Yeah, last question from Subhrata.
So this structure is visible in N2 very nicely. Okay, the structure that bar kind of oval structure that is visible in N2 very nicely. But in H alpha, it is there, but not at the very center. It is at the edges of the. So if you see the structure is completely coming here. But when you look at the H alpha, it is coming at the ends of the that region, not throughout the entire region. And the spiral is coming. Like it's basically when we see the star forming bars that we call the due to the orbital crowding, the most of the H alpha emissions are found in the at the ends of the bar. That is what in this case also we are saying. It is following the similar structure, but not throughout the galaxy. That's why we looked into the BPT and WAN, and it is more to the post HTTP where N2 is more dominating, not the H alpha. The structure is there, but H alpha emissions are not present in that region, but at the ends. But I don't know how to.
But do you expect the H alpha signature along the bar?
If it is star forming or so, then we can expect. But since it's not star forming, and the shocks are basically from the older populations. H1 observation, I think it has. This galaxy has been observed in the GMRT also. This is yeah, I don't know, like entire galaxy has been observed or that event gravitational wave, because there are lots of papers on.
There are also papers which claim that the gas bars are weak.
Yeah.
Comment on that. But anyway, so I think we are running behind the schedule, so we can wrap this like let's thank her once again. So next speaker is Rakshit Chauhan. Perfect. So I'll give you a warning of like you have last 3 minutes.
Yeah.
Huh?
Just a
Huh? Yeah. What you want to do is
Just raise or no? It's really intense.
Okay, you can start and I'll give you a warning after you. Okay, okay, fine.
Hello everyone, I'm Rakshit and today I will be presenting about the Starburst Galaxies. I'm on audible at the back.
Maybe a bit louder.
Okay, so I'm Rakshit and today I will be discussing about the Starburst Galaxies. So as we have gone through several lectures today, which are better describing about the merger events, how they are included, and the properties of galaxies. But I'm not going into the details, but I will just briefly give a overview about the thing. So as you know that the galaxy goes through a lot of internal as well as external processes, and out of the external processes, interaction play a crucial role in the overall evolution of the galaxy over the cosmic time. And as you can see in this simulation, so from bottom left to the bottom right, in an anti-clockwise direction, clockwise direction, it is signifying that whenever a galaxy is going through a merger event, so star formation rate changes in a non-trivial manner. It shows a very intense starburst activity as a result of coalescence and further leads to the quenching. But this is not the scenario as if we include the feedback mechanism into the scenario, like that the star formation is not changing drastically, but it would enhance by a factor of 1 or 2 times at that. And these kind of merger events are well explored in case of massive galaxies, and it is being found out that these could lead to the morphological transformation. Rearrangement of the stellar material could induce features like stellar streams, tidal arms, or other features, and it could also trigger the star formation activity as well as could trigger the AGN activity. And this kind of thing has been observationally verified by several studies. Some of them are here, but these kind of events for low mass galaxies are not well explored. Okay, so our aim is to find out what would be the implication of the interaction in the evolution of low mass galaxies. So why we are interested in dwarf galaxies? As we know that these dwarf galaxies are the most abundant galaxy population across all the universe at all the redshift, and most of the mergers are expected within these kind of systems only. Apart from that, they are considered as the living fossils of the early universe galaxies because these properties matches with that of the galaxies found in the early universe. Apart from that, as we know that there are very few studies which suggested a correlation between the star formation activity and the interaction in these dwarf galaxies. Still, these are few, but they suggest that there is a direct correlation between the star formation trigger as a result of interaction in these dwarf galaxies. This 2015 study by Stewart suggests that there is a direct enhancement in the star formation as a result of interaction in dwarfs. Apart from that, so the star formation in these dwarf galaxies are very well widespread and clumpy in nature in contrast to the massive galaxies where the interaction would be more efficient in case of the central region in spite of being widespread across the galaxy. And this has been explored by different studies like these are here, but this is not the overall case. There is one recent study by Chauhan, and he suggested that as a result of interaction, there is not always the case that star formation would increase or there is a positive implication of the star formation in these kind of galaxies, but there could be quenching as well. So it suggests that the interaction, apart from the interaction, there are several other internal mechanisms working that could influence the star forming properties of this dwarf galaxy, considering the galaxy evolution as a whole. So, this loading. So our scientific aim is to find out what would be the implication of interaction on the evolutionary properties of these dwarf galaxies. Apart from that, we would also consider whether we could discern the star forming efficiency or star formation activity, considering the case of a starburst event that is being triggered as a result of mergers or other starburst event triggering in other galaxies, which could be the result of some secular evolutionary processes within these dwarf galaxies. So, considering that scenario, we are taking care of the shortcoming of previous studies, and that's how we are going to further perform our studies. So, by going through various literature, we find out that these studies are not considering the post-merger dwarf galaxies as a whole in order to study the evolution of these dwarf galaxies. Apart from that, they are mostly concentrated towards the upper mass regime, like 10 to the power 9 solar mass or so. And as we know that the FUV is a better probe in order to understand the recent star formation activity, because it would probe the star formation that has been taken place within few 100 million years or so. So FUV could be a better probe in order to understand the recent star formation in these dwarf galaxies. Now, considering that into mind, I have distributed my project into two different criteria. First, I will introduce what would be the application of interaction on the star forming properties of dwarf galaxy. Then I would particularly look into the starburst dwarf galaxies, whether we could disentangle the star formation or spatial distribution of the star formation within merger driven and secularly driven starburst events. Okay, so the first study would consist about the FUV study of post-merger dwarfs. And for that, we are taking this bigger sample of dwarf galaxies, more than 6,000, and we are going to look for the Galaxy data, whichever out of this 6,875 taken from this Cadaver 2020 paper, and how much is available in the Galaxy data archive. We will just download the FUV data for all of these galaxies, and in order to detect the post-merger galaxies. So this tidal feature detection algorithm was applied in order to detect the post-merger galaxy. So if any galaxy is showing some tidal signature, we will find out that it could be a remnant of some post-merger event happened with these two dwarf galaxies. Okay. So as we know that the galaxy field of view is quite bigger and the dwarf galaxy size is comparatively smaller. So in order to detect the galaxy within the entire field of view of galaxy, we are using the Studento structure identification parameter in order to find out the galaxy structure, and we are calculating the star formation rate based on the flux estimated from the FUV luminosity. So coming to the results part. So we are estimating the SFR for post-merger as well as the non-interacting isolated galaxy. And these are the star forming main sequence for all of our sample of 6,200 galaxies. And by looking at the star formation main sequence, we find out that our sample is dominated by star forming galaxies. They are not dominated by particularly branching or starburst galaxies. Even though there are several galaxies which are lying in the starburst as well as branching region. So in order to make an estimate of how star formation is varying in the post-merger case and the non-interacting case, we generate a control sample of non-interacting galaxies such that it is matched well in mass and the redshift simultaneously. And we find out that in the post-merger cases, there was an enhancement of nearly 2 times SFR compared to that of the non-interacting case. Apart from that, we also find out that in the central region, and we compare the central region SFR and the outer region SFR for interacting and non-interacting galaxies. And we find out that it is more or less similar. It is not changing drastically as we observed in the massive galaxy scenario. So it suggests that these galaxies have shallow gravitational potential profile. So it may not be able to fuse the gas into the central region and trigger the star formation activity into the central region, but it is overall enhanced across the galaxy. So this is about the overall galaxy population. Now coming to the starburst review. As we know that the triggering mechanism which is responsible for the trigger of intense starburst activity in these galaxies are not clear. But there are some studies which suggest that there are few mechanisms that could trigger starburst activity in these galaxies. So it could be classified into external as well as internal mechanism. External include the tidal perturbation from some nearby massive companion, or if these dwarf galaxies are lying within some cluster environment, or it could be the interaction between same kind of gas-rich dwarf galaxies. Here, our sample is isolated in that sense. It is lying 1 megaparsec away from some massive galaxy. So the interaction we are expecting should be between the dwarf galaxies. Apart from that, there could be cold gas acquisition scenario from the IGM surrounding the galaxies. And there are several internal mechanisms as well. So we are considering that as a cellular evolutionary process. So it could be due to the torque due to massive star forming regions within the galaxy. There could be some feedback mechanism as well. And there are some other theoretical scenarios in which some triaxial dark matter halo could lead to the star bursting activity and bar driven. Like even though these dwarf galaxies have they are type of stellar bars and density waves, but there are some scenarios in which theoretical people have suggested that there could be dark matter satellite interaction or presence of these dark matter satellite would pressurize the gas in order to sustain the star formation activity in these dwarf galaxies. So in our case, we are trying to find out whether the star formation triggered due to these different mechanisms are considerably different, or whether it would be same. We can't discern in case of dwarf galaxies. So in that scenario, Thorpe et al. Did this kind of a study for massive galaxies, and they found out that in massive galaxies, in the massive starburst galaxies, the starburst was more prominent in the central region, and in case of post-merger galaxies. But if we consider the case of non-interacting galaxies, it was kind of more uniformly widespread across the galaxy. So this was one of the differences that they observed. Apart from that, they were clearly able to distinguish the star formation that has been triggered in the post-merger galaxy as well as non-interacting galaxy. But this study was particularly for the high mass galaxy. Yeah. So coming to the selection criteria, we are taking all those galaxies which are lying above the basket plus 1 sigma line. So these are considered as the star bursting galaxy. So we did a direct comparison of a star bursting post-merger dwarf galaxies and a star bursting non-interacting galaxy. We did not find any particular signature. So this could be due to 2 reasons. First one is the lack of post-merger dwarfs in the lower mass regime, and the selection criteria, because as you can see in this picture, there are several high mass and dwarf galaxies that are showing the evidence of the star bursting activity in their star formation scenario. So what we did, we just adopt a similar kind of criteria that has been adopted by Thorpe et al. So we compare the star burst with respect to the normal star forming region. So it is being applied for both the post-merger as well as non-interacting galaxies. And we find out that even though these kind of galaxies are selected based on the similar mass and the redshift and similar environmental condition, but the enhancement factor was considerably varying in case of post-merger galaxy as compared to the non-interacting galaxy. It was some 1.5 times higher in post-merger galaxy. So either it is due to the observed inherent property, or it is due to the selection bias that we are applying in order to select the starburst in our sample. So in order to further figure it out, we just did a spatially variation property, spatially distribution of star formation in the galaxy. So we divide our galaxy into different regions based on the galaxy resolution, of course. And we compare the star formation activity in post-merger and non-interacting, and we find out that even though there is a difference in the radial variation of star formation rate surface density profile, but we are not sure because the error bars are comparatively high, we consider. So we are not able to discern the property of starburst activity in post-merger and non-interacting blocks. Apart from that, we did a similar comparison. Okay. So this is by considering the similar kind of enhancement. So the enhancement factor for this part is like from 1 to 8, and then from 8 to 16 and 16 to 20. Even though we are not able to discern any difference in the properties of star formation in the starbursting post-merger and non-magnetic starburst. But there is a clear pattern that there is a radial decrement in the star formation at surface length in both kind of dwarf starburst. And this result has been well established in our other studies as well, in which we did a high resolution. Also, in which we did a high resolution spatially resolved study by using slightly less massive dwarf galaxies, and these results are lying well with this spatially resolved studies as well. So even though I'm I'm running out of time, so I will leave you with my summary slide. Summary is there, but yeah.
Thanks for the interesting talk. So maybe one or two quick questions. So we move to the last talk of the session. One or two quick questions. Anyone? Yes, please.
You mentioned the flow that R1, R2, R3. How did you decide that radial is a galaxy?
So the best possible resolution of galaxies either 5 arcsecond to 6 arcsecond. So our center region is diameter of 6 arcsecond in the center. We are not sure about the R25 or the RE of the galaxy. It was done within the resolution itself. So we took that radii, the minimum central diameter 6 arcsecond, and multiplied by 2 3 times. Because we can't go beyond that.
Just wait. So let's end like the speaker. We can keep the further question session for the tea break. So let's move to the last talk of this session, and this is called Jyoti Prakash. And I'll give you like in a 2-minute warning. Please stick to the time. It's beautiful. Rakshit.
Am I audible? Yes. Okay. Okay. So we have very good talks on the galaxy merger, like how to even the mother galaxy, and like how mother can do some where sometimes we can form some debris. So I'm going to talk about galaxy merger for dots. So as you know that like when two galaxies come closer due to gravity, they can distort each other material, gas and a star, and they can strip out materials from their outer disk, and they can form some structure like grease, and there's some Tidal structure. Okay, so these tails and these can be like say very around 100 kiloparsec long. So another thing it can happen that it can the gas stripped from the disk can collapse under gravity, and it can form some dwarf galaxy structure. Okay, so they are called some non-structured dwarf galaxy structure. because they are formed from second materials of this galaxy, and they have some different structure in terms of metallicity and the dark matter. So we are going to explore some properties of this non-classical dwarf galaxy, also called tidal dwarf galaxy. And these tails and bridges are like more prominent in progress encounters, because in progress encounters like we have the same velocity alignment. So the time represented in more per counter. So like momentum keeps pulling materials for a long time. So in this scenario, we have like longer tidal tails and bridges. As it can be seen in this galaxy, there are two tidal tails, and in this galaxy, we have like a very big tidal bridge, like three interacting galaxy system. So in particular, I have studied a galaxy called Guitar Galaxy. So due to the same resemblance, it is called Guitar Galaxy. And here we have this RV image from HDSS. So you can see here that like the shape is similar to guitar. So you can see that like NC series 661b is like Liquid Galaxy, and this is like Star Galaxy, and there is a tidal bridge here, which is around 100 km/s long. Okay, and at the tip of this tidal of this, there are two galaxies. This is north part, and this is south part. Okay. So these TDC are also like considered in the computer science. They are attached to the chemical code of the mother galaxy in the mother womb, right? And so this galaxy is around 127 megaparsec from us, at 0.29. And we have this FV image. So which tells us that we have some where these PDC are like FV nodes. Basically, this tells us that these nodes are star-forming galaxy on the 100 megayear scale. So basically, they are like star-forming galaxy at the dwarf galaxy. So for this study, we have taken data from SOSAT FV filter, and then we have SPSS optical and near filter, then a SPSS telescope. Okay. So SPSS is 2.5 meter telescope in using LJ bands, and then for one of our TTC, we have a spectrograph from SPSS also spectrograph, which has around 200 to 2.5 K. And finally, we have a spatial data from either 1 to 4 band, from 3.6 micron to 8 micron. And so here is we have one advantage over this Galaxy data, okay? Because VIT has like very high resolution around 1.67 arc-second compared to 5 arc-second of PSF of Galaxy. So next, since we are like using multi-wavelength data, right? So we have to compare images on the equal footing, okay? So for that, like we have built PSF, and then we have convert all images on the equal footing. I mean, on the same resolution scale and on the same PSF scale. Okay. So basically, we have either 4 band is a watch band PSF, which is around around 2 arc-second is PSF control, right? So what we have done, we have first like we build a PSF from a bright star. So you can see this image in the PSF modeling using Moffat function, right? So we have data, then this function model, and this is the density goal, okay? So and the PSF is around 1.2 arc-second for SSS R band. And so like once we like build the PSF, we are going to convert all PSF into the IRF 4 band PSF, right? So which is the watch band PSF. So like once like we get PSF conversion, so we convert all PSF using this PSF matching color, right? So basically, like we have say we have SSR band PSF is very narrower, and we have fat PSF of either 4 band. Okay. So we build a kernel which transforms SSR band PSF into either 4 band PSF. So basically, we are going from thinner PSF to a broader PSF. So which matches the resolution of your all images, right? So like once we like got the kernel matching now, then we convert all images from SDSS to VIT to either 1, 2, 3, 4 band into the PSF of the IRF 4 band. So here you can see that there is a PSF match growth curve. So here like the PSF, I mean this tells us basically that like how your PSF matches well constrained. Okay, so basically see that like your PSF from R band and IF4 band both matches, right? It means that your PSF match is very accurate. So like once we have like images of all protein, so we use source extractor. So basically it extracts the object from the crowded source, right? So for that we have used this parameter, like how much minimum area should detect, what is some sigma threshold. We have given some filter name like smoother like this. Then we have given the PSF, and then we have some given like how objects are not going to be blend into each other. So based on that parameters, we have extracted our object. So here you can see that we have the bridge is our one object. Here we have this not TTZ here. There. There's one more TTZ called soft TTZ. It is a compact object, right? So these three objects we have chosen for our study, like one bridge and two dwarf galaxy. So okay, so next we did some 2D Galactic modeling. So basically, Galactic modeling does is that it takes your original band image and then it takes a parametric model and then it convolves with the same band PSF. So basically, PSF pollutes the image. Okay, so in that case, you can minimize your residual to get your best fit. So for Galactic modeling, we have used lopsided Sarsic disk, okay, n equal to 1, and this gives a size of around 2.2 kpc for north TDZ, and for the south TDZ, we have used Sarsic modeling, so which gives in 1.27, and which gives a size of around 1.0 kpc. So basically, our like north TDZ, south TDZ like more compact than our diffuse TDZ of north side. So basically, this tells us that these objects are really in the dwarf galaxy scale on the size. So next, we did Seagull modeling to find the properties of this galaxy, like shadow mass, dust mass, stuff. Okay. So we have say 3 TDs, right? We have 3 tidal component. So we have used some certain IMF. We have used dust extinction law and Nathan model. So this TDZ contains like 2 populations. Right. So one from like older from the fancy, and one is that they're like start, so they have like younger population. So we have modeled this TDZ using a double extension. Like one is older and one is much younger. So in that case, we have 3 component density model. So this is for north part, this is for south, this is for the east part. Okay. So we have obtained these density masses from there in this dot range. 5.7.3.40.82. So we have highest mass TDZ is the north, and we have the south TDZ is 10 times roughly, less. And then we also use this current mass lesson from Bell and Young here to get this mass. So this mass is different from 0.2 to 0.3x, which is compared to ACT. So basically, this tells us that like we have this TDZ are like dwarf galaxy and having mass less than 10 or 9.5 solar mass. So yeah, once you have like Keshri fitting, we can get some this SFR on the 100 mega-year scale. So then like we plotted this SSFR versus image star. So on that plot, you can see that we have divided galaxy into 3 regions: star forming, green valleys, and phase. So you can see that we have 3 regions. So our TDZ lies in the star forming regions. Okay. So basically, they are like star forming galaxy because like they are emitting from collapsing of their gas from the outer disk of those galaxies. So due to that, like they are getting a star forming scenario by collapsing their gas under the pressure, right? So we have also SFR measurement from Astrosat band, right? So we have some north. This is for these, and this is for okay. So basically, this tells us that like we have series like a sharpening galaxy. So next time we do this spectral fitting of R105. So from there, like I obtained this double decrement, which was like used for correcting your nebulous extinction. And we also found this again 4001, which suggests that like this TDZ like having younger but like less than 1 gigayear old structure. So we have a strong H alpha and H beta. So which tells us that these galaxies like having recent establishment history on the scale of around less than 10 megayear. And we also like use sodium line to measure like the dispersal of a star using cool gas or cool stars. So then we like look into the like how the metal content varies from the normal dwarf galaxy. So we found at using two different methods that these KTZ are like more metal rich compared to the classical dwarf galaxy, which are made from the fission gas. So you can see the mapping from all the objects. The galaxy, this is like KTZ. So basically, the message is that these structures are comparatively more metal rich compared to your classical dwarf galaxies. So and then like how these metallicity like have similar value. So the material is like going the outskirts of this galaxy from here and there. So this metallicity compared to like 2/3 of the solar metallicity. So this is like one like conclusion that this galaxy are like made from these objects. Okay, the materials are like going hard from here and they're like also making on a star formation. So basically they're like adding their own metallicity and on top of their parent galaxy. So that's why like they're like more metal rich. And so like they like want more, it's like so like if you find a KTZ like having more metal rich, then it might be a KTZ candidate in general. So next I did this delta mass measurement of this galaxy. So for that we have a star from SCD fitting, and then for measuring dynamical this is a chemical mass of around 1.5 to 1.6 solar, on that residue. So basically, this tells us that this galaxy chemical mass is like similar to this baryonic mass. Okay, so there's like not much dark matter potential is there. So basically, they're like lacking dark matter content in their galaxy. So the reason can be like explained that like these KTZ are like a small object. So they have like few patterns of like escape velocity. And also like this galaxy like the diamond halo of the galaxy, but they cannot trap their dark matter particles because they have a high velocity. But also like a small dark matter cannot trap, but like large sum of dark matter cannot trap. So that's why they are like dark matter efficient galaxy. So compared to like the number of galaxies that are very little dark matter in those galaxies. So yeah, thank you. So I will stop here and this is the conclusion.
Time for some quick questions. Yes.
Okay, so like what we try to compare now. So we have measured like masses from like two different methods. Okay, so this also like uses the factor of awareness, so that's why we use the factor like compare these masses. Then like we have done this one for the also. So this gives little higher masses. So just to compare these two results, we have like we can also give different angle, but for comparing results, we have chosen this arbitrary.
Any other questions? Yes.
Each of these big galaxies, any question if you have high density gas, actually have like real star formation, how do you differentiate it with the dwarf? How do you explain it to the dwarf galaxy or just the not star?
Okay, so if I am so like other about like how KTZ are different from the dwarf galaxy in terms of SFR.
No, his question was probably like how you can like tell it is a dwarf galaxy rather than a big blob of like star forming
Okay,
or, which is being stripped from other, and then because of the compressive tidal field, it triggers the star formation.
okay, so we have done it like 3D model. We are using Galactic model to model this galaxy, get the size of this galaxy. So these like size and matches from the dwarf galaxy. So on that basis, then that they are bigger structure. They are not big galaxy or bigger structure. We have modeled this galaxy using rapid 2D modeling. So this gives us the size of the galaxy. So in this question about this, okay.
Just one comment. There are these ultra diffuse galaxies, right? Some of them are supposed to be dark matter. So then put your work explain those as tidal dwarf galaxies.
Okay, so
Maybe they form the tidal dwarf galaxies.
yeah, so like if you can like if it is okay, then you can like look for some metallicity. So like if they're like high metallicity, then they may be TDC. There's like one thing to like look for TDC candidate. If they're like high metallicity, then there might be a TDC galaxy. Else not. So like yeah, so the gas phase metallicity is like the key to identify TDC.
Oh, that's good.
No, gas phase metallicity.
Yes.
So if like high metal content around 8.54 plus log by S, then it may be possible TDC candidate.
Just one question here. How do you get an asymmetric exponentially modeling?
Okay, like you have Fourier mode m equal to 1.
Okay, any other questions?
How do you explain radical mass using various?
Yeah.
Is it applicable there?
Yeah. So like we assume that like this is like very hard is located from the this galaxy, okay, down 1 kilo conflict from this BTC. So it is like if we want to have this delta billion, then like we use density profile rho equal to 1 by r square, isothermal profile, and then we use the sodium lines from the dispersion. So from there, like we have this equation. So we got the dynamical mass of yeah, I think it will, but like if it is like analytical decoupled, then you can apply this velocity, else not. So we assume that it is like very far from this planet, and they are in equilibrium. They are not in the interest of their parent galaxy. So they are kinematically decoupled. That you can apply velocity.
Okay. Is there any other question? If not, let's thank all the speakers of this session. We are very much. It's time for tea and coffee.
Yeah, tell them that.
And we'll reconvene here at 4 for the flash talk, poster flash talk.
But the tea is in front of auditorium.
Outside. Outside auditorium. Okay. We can follow later. And then. You control
But,
He has the list of speakers.
Will come under.
This kind of things. The duration is 4 weeks. 4 weeks. So 3 plus 1. Yes. But the paper of okay, we have to get it. Welcome back. We have five flash talks that in case you will know the order, and 4 minutes per presentation, and I will request 3 minutes and leave 1 minute for question. If you split that 3 to 4, then question is lost. So the first is Risha. I will be talking about tidal modification of gravitational instability in galaxy mergers.
Have you all ever wondered what will be the effects of tidal field on an astrocloud due to the presence of galaxy mergers? Now, astroclouds were defined by Jeans instability criterion, and this research was extended by Jauhan, who introduced an external potential. So, on doing so, the author obtained this dispersion relation where T0 is the modified term and it is the radial tidal contribution due to the external potential. So if T0 is positive, that means the tidal fields are disruptive in nature. If T0 is negative, it means tidal fields are compressive in nature. Now in our case, we have considered 2 galaxies, as we can see here, a host and a companion. So we have derived the tidal field for the companion galaxy, which is this. As we can see, it depends on the gravitational constant, the mass of the companion galaxy, pericentric distance. F of t is an anomaly which tells us about the orbital phase angle of the companion galaxy, and theta is the orientation angle, which is basically what the angle made by an astrocloud present on host galaxy with the merger axis. Now, at the pericenter, which is basically the distance of closest approach, f is equal to 0, which is shown in these 2 plots at f equal to 0. This is the pericenter. We have also obtained a critical angle, that is 54.7 degree, at which the tidal field vanishes. So, like if this 3 cos square theta minus 1 is 0, then this thing vanishes and that angle is 54.7 degree. Above and beyond this particular angle, the nature of tidal field changes. Now, these 2 plots here shows here we have plotted the ratio of job mass to Jeans mass, or the job length to Jeans length by orbital phase. Now, in these 2 plots, we can see at theta equals to 90 degree, the ratio is less than 1, which means that job mass is less than Jeans mass, or job length is less than Jeans length. This physically means that the astrocloud will collapse at a more smaller length or smaller mass. So the tendency of collapse is more, hence the nature of tidal field is compressive. And at this critical angle 54.7, we can see that the ratio is equal to 1, which means job mass is equal to Jeans mass and job length is equal to Jeans length. Thus, this is the critical angle where the existence of tidal field vanishes and the astrocloud will follow the classical Jeans instability criteria. Moving on, these 2 plots here are the imaginary and real roots of the modified dispersion relation. This is the growth rate of the instability. So as we can see, as theta increases, the growth rate of instability increases, which means that the astroclouds will get destabilized. Hence, the tendency to get collapse is more, and hence the nature of tidal field is compressive. And this shows the oscillation frequency of perturbation. So here, as the theta decreases, theta is decreasing. As the theta decreases, the oscillation frequency of perturbation increases, which means this leads to stronger restoration force. As a result, the astrocloud will stabilize and the nature of tidal field is extensive, that is disruptive. This plot is a variation of tidal field of companion galaxy with orbital phase and orientation angle. As I have told before, at the pericenter f equal to 0. So from here we can see at the pericenter, the tidal fields are the strongest and they fade away as the two galaxies slowly drift apart. And the orientation angle from here we understand that as the theta increases from 0 to 90, the nature of tidal field goes from disruptive to compressive. And how do we understand that? Tidal field is negative for compressive and positive for disruptive. And this plot here shows the variation of tidal field of companion galaxy with separation distance, that is the distance between the two merging galaxies. So at theta equals to 0, tidal field is positive, that is showing disruptive nature. Theta 90 it is negative, showing compressive nature. And critical angle, it coincides with the 0 line, which just means tidal field vanishes. And gradually, if we increase this distance, these two curves will tend to 0, indicating that as the two galaxies are drifting apart, the effect of tidal fields will reduce. So to conclude, here we have studied that due to merging galaxies, the instability dynamics of astrocloud depends on the mass of companion galaxy, pericentric distance, the separation distance, orientation angle, and the orbital phase.
Next speaker is Ayush Hazarika, revealing dark matter stored in neutron star anisotropy, a Bayesian approach.
Have you all ever wondered what will happen if dark matter is trapped inside a neutron star? To give a perspective, neutron stars are one of the most densest objects in the universe. For example, if we hold Mount Everest in a tablespoon, that's how dense a neutron star could be. And for such high density, there is a degeneracy pressure inside the neutron star, which acts against the gravitational force of such compact objects. Now, if we replace few of the baryonic particles with dark matter, then dark matter won't be contributing to the degeneracy pressure as it does not interact with normal matter. So what will happen? The degeneracy of a neutron star will be less than a pure baryonic neutron star, and hence what will happen? Gravity will overcome and compactify the star further. Because of this, we can see in this plot the dotted lines are purely for baryonic cases, and the entire Bayesian posterior is shifting towards the left, towards larger mass in smaller radius, which proves the compactification of the neutron star. And once a neutron star is compactified, the tidal deformity number will reduce. As we can see in this plot, the dotted line is for the pure baryonic case, and the entire posterior is for the dark matter admixed neutron star. For this, it is reducing, which means the resistance from the neutron star will be more towards tidal disruption when two binary neutron stars are revolving around each other. So there will be more resistance by such dark matter admixed neutron star. And further, we did the entire Bayesian constraint on dark matter parameters, on its coupling strength, on the fraction of dark matter that can be possible inside a neutron star, as well as dark matter mass and the mediator mass. So we choose a fermionic dark matter model, and for that, the current data was not able to put good constraints on that. As we also did a base factor study. What it means, if the base factor is above 10, then we have strong evidence that such systems exist. But in our analysis, we found none of the base factor was above 10, which basically means that the current data does not statistically favor a pure baryonic neutron star, neither a dark matter admixed neutron star. So with the current data, we cannot distinguish whether we have a dark matter admixed neutron star. And using for this Bayesian analysis, we use two types of data. One which is coming from observation, NICER, and another from GW17017 from gravitational waves, which gives us information on the tidal deformity of such systems. So till date, we have only seen one neutron star merger, which we are very sure that it was a neutron star. After that, till now, we have not observed any more neutron star mergers in gravitational waves. So we have some limitations with the data which we have. And because of this, we are not currently able to distinguish whether we have dark matter at neutron stars. So what's the future scope of such research? So what we are hoping with the upcoming new NICER 2 and Athena and other observational telescopes and all, along with the gravitational wave signals, we might be able to distinguish such neutron star, whether it is possible for such systems to be detected in such scenarios, and why we will be able to detect through gravitational waves, because gravitational wave signal will be very different for such stars, because we can see it will be having less tidal deformity number, so more compact. So if we have a pure baryonic and a dark matter neutron star, both tidal deformation will be different. Observationally, we will be thinking must be the mass, but if there is a stark contrast between the two, then we will know for sure that this systems exist. Thank you. Thank you.
Next talk is about possible class 3 simulation of iron transformation class of
Good evening. I'm going to introduce the neutrinos first class. That is, can the supermassive binary black hole candidates produce the neutrinos? That is detected by the telescope ISQ. Now, the motivation for this is that we know cosmic rays, but we don't know its origins yet. This is because as they are charged particles, and we don't know the exact magnetic field outside in the extragalactic medium, we cannot trace it back to their sources. So we'll use gamma rays and neutrinos to search for these origins, because they will be undeviated due to this magnetic. Now for this we use the neutrino data. From neutrino data from telescope ISQ, that is in the South Pole. It is in the Antarctic region with it is nothing but 1 kilometer cube of ice with digital optical modules or photomultipliers embedded in them, and this detects the Cherenkov radiation that is emitted by when the neutrinos interact with the Earth's material and produce their corresponding lengths. And this is the map of the schema of the neutrino data that is detected by the ISQ. The blue gradient is the neutrino ISQ neutrino data. This is the right assertion and the declination with respect to the equatorial coordinates. And the red dots are the supermassive binary black hole candidates that we got from different catalogs. Now, the question: can these SMBHP systems produce these neutrinos? There are multiple models which explains this production of these neutrinos from these SMBHP models. One of the main models that we considered is from this paper, by Jarowski and Julia Becker and Peter Wehrmann. The idea is that will come close to each other and will start interacting through dynamical friction. And after this dynamical friction, they go into a problem known as the final parsec problem. There are multiple ways in which this final parsec problem can be overcome. And once this has happened, they will come at very close separations than the parsec range. And at these close separations, the jets of these supermassive black holes will not be aligned with each other properly, and they will try to align with each other to reduce the energy. And while aligning, they will span over the entire space around them. And as the galaxy merger has happened, there will be a lot of debris and destruction of the stars and a lot of gases in the environment. And when these jets align with try to span over the entire region, it will have the proton-proton interactions and proton-gamma interactions, which will in turn produce the pions that will decay into the neutrinos. And these neutrinos are the ones that we expect to be detected using this ice cube neutrino data. Now, there are also other models, one involving a post-merger model and shock mechanisms as well. But in our paper, we mainly focus on this model, although this is a model independent analysis, so other models may also produce similar effects. And how we got these SMBHP candidates, as we know, we expect the gravitational waves to be the major area for this detection of this SMBHP candidates, but we don't have it in terms of electromagnetic indications like spectroscopic, photometric, and other areas. Now we use a stacking analysis, that is, we define a quantity test at 6, which is nothing but twice of log likelihood, and we try to stack multiple sources together and see the total diffuse neutrino flux that we detect from the ice cube. And we this stacking can be done in multiple methods. We use 3 kinds of analysis. One is neutrino flux, that is from the model dependent area, and next is volumetric, which is that higher the electromagnetic radiation, the more is the neutrinos coming from the sources. And finally, uniform, that is all sources contribute equally towards these neutrinos. We have also done 2 analyses. One is only spatial correlation, and another is spatial and energy correlated stuff. And this one of the results. This is one of the results of our paper. In this one, I just like to mention that the left figure shows the energy weighted flux versus the twice of log likelihood. And the peak one, the peak represents the test at 6 quantity that I'm saying. That is the significance that neutrinos can be correlated with the SMBHP systems. And the results of our paper are here. And as you can see, the neutrino flux shows a higher significance of around 3 sigma in the spatial only analysis and around 2.5 sigma in spatial energy or combined analysis. And this slightly indicates towards a possible correlation between the SMBHP candidates and the neutrino data of the ice cube. And further data are needed to confirm this indication and strengthen this set. We have published our paper as preprint in astropage.hc, and this is our archive ID. You guys can check it out. And me and Subhrata will also be available in the poster presentation. Thank you.
Because of limited dimension, the final percent problem is overcome.
No, not. Final Parsec problem can be overcome with multiple methods, not exactly neutrino efficient.
The next presenter is Aditi. We'll talk about the impact of dark matter heliospace on the part formation in thin and thick type galaxies.
Hello, I'm Aditi from IIT Kanpur, and I'm working on the impact of dark matter heliospace on the bar formation in thin and thick Milky Way type disk. So we know that that Milky Way disk can contain
Louder.
Hello.
It's louder.
Am I audible now?
Come closer, yeah.
Okay, we know that the Milky Way can contain both thin and thick type of disk. So previously the studies have single disk. So we are working on 2 disks separately. So from the cosmological simulations, we know that the dark matter heliospace typically ranges from 0.0 to 0.1. So we are taking 5 models, approx 5 models, and we are evolving our models with that heliospace. Simulation setup. So we produce equilibrium models with the help of a gamma that is written in Python. And then we have evolved our models in Gadget 2 over a time scale of 10 GHz. So yes, in my preliminary results, I have measured bar strength as well as Foxy Pinnet strength. So we have used Fourier for M2, M equal to 2. So the key observations are like we can see as the bar form after 2 to 3 gigayears, and the bar strength is strongest at, I guess, around 8 to 10 gigayears. And we can see that in the thin disk, the bar strength is higher, and in the thick disk, the bar strength is lower. And we can also see that the vertical buckling is higher in the thick disk, and it is lower in the thin disk. So yes, we can see that the increasing halo spins slightly affect the bar strength as well as the buckling action. So we can conclude that the bars form naturally in the thick as well as thin disk, and we can see that thin disks form stronger bars and the thick form weaker bars. And the halo spin enhances the angular momentum transfer. And in future work, we can study the pattern evolution, pattern speed, and analyze core rotation radius, and even include gas particles as well. See the impact of halo spin on kinetic disk. And we can compare our results with the real Milky Way galaxies. So that's all. Thank you.
Have time for a lot of questions. Yeah, question please.
The last one. So whether the thin disk and thick disk are separate cases, or does the same galaxy have a thin and a thick?
The same galaxy have the thin end.
Okay. So the bar is buckling in the thin disk at the same time it's buckling in the thick disk.
Yes, but it is weaker in thin disk and it's stronger in the thick disk.
You want the same question? Thank you very much. Last talk is by Abhay. We'll be talking about characterization of unclassified galaxies.
Good evening, guys. My name is Abhay. I'm studying MSc in Acharya Institute. So normally today my topic is very basic characterization of unclassified galaxies. Actually, we know that we have access to very large data sets like PAN stars and DAISY and all. In that, we know that most of the galaxies don't get their characterization because most of them go for the highly classified galaxies and all for their research. So I took the opportunity to do my research in this. So I have taken 6 data sets, 6 different data sets. So normally let's go first with the introduction. Like galaxies have their own different type, like identity in their morphology. It can be elliptical, it can be spiral, it can be irregular, different. There are other it comes same for the merger also. So when the merger happens, they can become irregular, and there most of the gases lose their angular momentum, due to which the gas compression will be in the central part. So to find all those properties, I have chosen the data sets from PAN stars, DAISY, Galax, WISE, and DSS, and also for I can show you here. See. From Galaxy and another one from MUSE. Why I took these 6 is for using the WISE data sets, we can actually find out the gas clouds or the dust clouds which are there, which are formed during the galaxy merger. As we know that during the mergers, a huge amount of dust clouds can be dispersed in different directions, and during this, there is a gas compression in the central part, and these emitted light can be absorbed by these dust clouds and later emitted as infrared. So that can be we can observe that using the WISE telescope and also the MUSE telescope also. And later when we go for PAN stars, it's used mostly for morphology. It is an optical telescope. Here you can see that this is actually two different galaxies. This is NGC 169 and this is IC 1559. So this is actually pre-merger. We have been talking about post-merger and galaxy merger from the morning. This is actually a pre-merger. Okay. In next millions or billions of years, they are going to merge. But due to the corner connections, they are actually tidally distorted for now, which can be observed. Like here you can see the tidally disturbed parts here, and these actually help us to understand how the starburst activity is going on in the galaxy, like during the pre-merger stages and all. And you can see the Galax observation. Galax is actually used to study about the star forming, like the newly star forming regions. So that is actually a UV light, like which is taken by the Galax like data set. And DASY is normally used to study the redshift and its spectral properties. So actually using this, we can study different properties of like the galaxy mergers and even also about the galaxies. The reason for taking all these 6 types is few of the galaxies don't have pan stars and few of the galaxies normally don't have DASY. So if you combine all these, you can almost get the most of the information about all of the galaxies.
Thank all the speakers.
Yes.
Yeah, so now there will be a hands-on session. So, Amrita. So we have shared that hands-on instructions with you. So I hope you have installed those packages. If anyone ever faced any issue, just let us. Am I audible?
All of you got the PDF now?
Yes.
Okay.
Can I connect my camera? So how many of you have DS9? Nearly everyone, I guess. You have anyone doesn't have haven't installed DS9? QFix view? No DS9 or QFix. You have DS9. So I'll be just showing.
Those of you who don't have it, maybe you can sit next to someone who has PS9. Like that, you find someone who has PS9.
Yeah, it sounds.
I saw that very interesting. I didn't believe the note. I know that. See, you have. we'll take it static. And now we go to this. They did. So this is that act. Okay.
So there is some problem. I had only 2 slides to show what is IFU data. So you might So we will start first hands-on session. So today we will be looking at a 3D cube, data cube. So it is also called as IFU, integral field spectroscopy or unit. So how many of you have used 3D data cube? How many of you have used 2D data, 2D cube, not 2D cube, 2D data? Most of you might have used, right? Like most of the FITS files are 2D. But there are also 3D data cube, which also gives the spectral information for each pixel. So what is integral field unit spectroscopy? So you guys have if there is a point source, it's easy to get a spectrum and do a analysis. But if it is an extended object, it is very difficult because each point in an object gives a different information. So it is necessary to get a spectrum of each point. But like with the usual spectroscopy technique, it's very difficult. So there is something people have like in radio and all, people have been using a data cube. But nowadays there are like many in this kind of technique. There is integral field unit spectroscopy is like used everywhere. So this is like a method where signal from each pixel. So you have a fixed file, you know, like image you have, each pixel give you a flux. So those fluxes will be fed into a spectrograph, and for each pixels you will get a spectrum. That is called that instrument which does this is a integral field unit or spectroscope. Integral field spectroscope. So you can see here. So where is this? So this is like a spatial dimension. So what image you are seeing? This is the spatial, like just a fits by just an image you are seeing. But there is a z-axis which gives a spectral dimension. So this is a spectral dimension. So here you will get a spectrum. So I have one more slide for this. So this is the principle of integral field spectroscopy. That is like they will slice the image, and each slice will be fed into a spectrograph. You have information, spatial information. So those flux will be fed into a spectrograph, and it will be dispersed. So each slice will give you a spectrum. So that's what here you can see. Like there are different slices, but since we need each pixels can be considered as a slice, and each of them have a spectrum. So you can see there is a spectrum from image each will have. So now since it's a hands-on session, I don't have many more slides. So what I'm going to do is just like when you are getting a cube, you are not directly going to do analysis, right? Just not going to code. So you want to see like does this galaxy or any object have the information what you want, or is this a kind of object you want to look? So for that, first you want to see some astronomical visualization app or something like that. So for that, there is like a DS9 and QFIX view, which can usually can be used to visualize the data cube. So I'll be showing both of them, and I'll show how you can use and do some basic analysis before going to use before you can do a rigorous analysis using Python or other. So have you all downloaded what like MUSE and MaNGA data what they had sent? So there must be a file called NGC 0000. Oh, you can't access it.
Is it this is acceptable? Is that not a spacing issue?
I think so now we know.
Is anyone else facing an issue for downloading the data?
It's a Wi-Fi link.
So how many are able to download the gateway here? Can you raise your hand? 24? Right? So how many are able to download the data? That fits right.
NGC 0000.
What about the others?
If there is any problem, you can say. Otherwise,
yeah, Saili is there. You can just ask her if you are facing any issue.
So I will just.
They're saying the ideal Wi-Fi is very deep.
Okay. For that, I think since I mean we have a very limited time, this will be also recorded. So you can go back and look at it and do it. So I will just show once like how you can use DS9 to do visualize the data. Okay.
No, they are not helping. It's Wi-Fi or not helping. But she's corrected Priya. Can you just watch, I think?
Yeah, you can just watch. You will be having this in YouTube, so you can again go and check this whenever you get it out. That's what I also do many times. So if you are using So, Chandan. So wherever you are, I mean, for those people who already have data, wherever you have a NDC 0000.bits file, you can open that file with like, if you just, okay, I'll just show, if you just open a cube, like if you just, as a usual thing, if you go there and if you just check NDC 000, how it looks like is like this. It's just a slice. So you are not getting the complete cube information, right? So what you are seeing. I just see this. So what you are seeing is just a slice, right? You are not seeing a cube. Are you seeing a cube? No, right? So what we can do is go to frame, open a new frame. So here you can go again, open. NDC 0006. So now you get, again, it looks like a, what do you say, slice. But if you change here, you got another thing called azimuth and elevation. So if you change here, you can see a cube. So from 0, take it to 1. It's slowly including. Let's check this 1.
This all of it is being live streamed on YouTube and therefore is recorded, and the quality there is much better. Even if you can't read out anything here. So I think the YouTube links have been shared with all of you, so you can always access it later and later. Or either you can go to YouTube IDs and Guru, so there you can find it.
So you see here, I have changed azimuth and elevation to 1, 1 and apply. So it takes some time to change here. So now you can see 3D cube, right? Cube, right? It's slowly coming. So still you can see a cube. You don't see information inside, but still you can see the cube. So I'm changing the color and I'm scaling it. It takes some time. So let's see. So now, first you saw just an image, but you got to know the data is not just an image, 2D image, but it's a cube. So the z-axis, what you are seeing is the spectral axis. Then you can see even here, there is something here down, cube. So there you can see a different wavelength. I mean, here only you are seeing 4750, but you can, when you move it, you can go to different wavelengths, different slices. Okay, it's loading now.
Loaded.
So you can see that at some wavelength, there is some information. So it's not just a single, like what we saw, it's not just like that. Each wavelength, the image keeps changing because like each there might be an emission in some wavelength, there might be absorption in some wavelength. So each wavelength, we will see some kind of features. So okay, now I think it's still loading, it's taking a lot of time. So you can like make it smaller, visualize it better. Let's see, here it works, here it takes some time. So now you can see it here. So let's see. I showed you like there was one more.
Is there a slice in between? There's one slice.
Yes, yes. So that's like at some wavelength there is some emission. So that's why they have like we can see that at some slice. So if we like you see this, if you go to frame, you can get the cube. So in cube you can see that you can go through a spectral axis. Like if you move this, you can see that is moved. Can you see there? There is some box moving along the spectral axis.
Box is not moving though.
It's moving.
It is, but the screen is not good enough to show.
Can you see?
Box is moving.
Yes,
yes. Box.
So you can see at this particular wavelength, that is around, I mean, you can't say particularly this wavelength, but around this wavelength, around 6627 angstrom, there is some kind of emission. So if you see it's closer to H alpha. So at H alpha, we can see some emission around H alpha wavelength. So what we can do is, it's difficult, we know that at some particular point we are seeing emission, we can just crop it and get the cube only for that place, that wavelength. So if you go to zoom, there is something called crop parameters. So in 3D, again you get a wavelength, so then you can put the wavelength around that region. So it is like 6627, right? So we can take around 6625 to 6635 and apply. So what we are seeing, we are seeing the slides, so we can again change the elevation and azimuth. We can change some degrees.
Elevation is what? Above central part.
Yes, yes. How we which angle we want to look, that would be us. So now we can see here.
Box around that way.
Yes, yes. This is the box around that wavelength. So we can play. Now you can see this cube have only limited wavelength range from 6625 to 6635. So if we play, we will only see around that wavelength. So all what we can do is, but we are not getting a complete information, right?
Yes.
So we can just go to slice itself and so like to visualize the cube, you can do like this. You can take you can make it a 3D cube and see where exactly you are seeing the emission and take a cut and take the cube. You can just take that cube and do the analysis. So I'll just go to slice and show you what kind of analysis you get. So you can just open now. Since you just need a slice. Stop. Okay, just open new frame. So now you are just seeing the slice. So we know like at what wavelength you are getting the emission. So I will again crop it. Was around 6625 to 6635. So let me apply that. After that, we can like and can play to see if there is any connection. If there is any difference in the electron. Not see that. I will just aid it. So this is over what wavelength range? This is around 6625 to 6635. So we were seeing that emission, extra emission in that region. So we will try to see if we find something in that. So after this, okay, if you after getting a region of your interest, you want to see, I told you, you will get a spectrum in each region, right? Spectrum. So in DSN, how to see the spectrum? So let's go to frame. Let's go to edit and choose the region. Choose the region of your interest. Let me take central one itself. And go to analysis. If you go there, you will get a plot 3D. Then you get a spectrum. So since I have put here, taken just a short wavelength range, we are seeing this one. So if we take a long wavelength, complete wavelength range, you will see a complete spectrum. So we can even check that. So edit region. So choose some region. First go to edit. First go to edit. Then go to region. Choose any region. Double click on that. Analysis. Plot 3D. You will get a spectrum. So you are getting spectrum over a complete spectral range. So if you crop it, you can just see what you want. I mean, wherever you are interested. And now you are seeing the complete wavelength range. And you can here move the region. And you see that spectrum is changing. Can you see? So wherever you are interested, you can move and see like how the spectrum looks. So for the basic analysis, that before going to like doing in Python or something, you can just look here and see like at the region of interest, you are finding what you want. So you can see some strong emission here. You were saying like 6635.
So if there was some star forming cloud there, you could go there and see enhanced emission there.
Yes. And then you can go to edit and zoom also. Like again, like if you are interested, you can just go to particular region and zoom. And you can even check the statistics. Like you will get what is the minimum flux in this spectra, what is the maximum flux in this spectra. So here itself, in analysis itself, if you go here, you can see the statistics. Then you will get all the statistics, like minimum, median, standard deviation. If you take only that part of spectrum, it will show for that part. So you can use this also. And you can even visualize the data. So here there are like, so if you show data, then so you can see like data points and all it show. Symbol. So each point where the data points are, it shows. And you can save these data points also. So here you have this save data. So if you save data, you get a spectral information, that is like flux and what is this? Wavelength. So you can see one more thing is that whenever you check any astronomical data, first you have to do is check their header and get the information of the unit, what's the unit of the flux you are getting or any information you are getting. So you will know what you are after. Like if it's velocity, it will show kilometer per second or meter per second, and if it's a flux, it will show angstrom, like some flux unit. So it is very important to check the data. So you have here two data. This is like general thing. So you have to check the data. So we don't have time. So this is like some basic analysis I showed you.
So does anyone have any questions?
I saw those two peaks for staff. Why do you have particularly good peaks with
Like it's a plate itself emission. Emission.
So each line gives a different information. Like S alpha is for the star formation, and two lines if there is a dome present here, that the will give you information. If there is a outflow or other high ionized indicators are there, then you have to check the O3. So the spectra gives a very useful information depending on the what thing you want to see.
Like ionization information you will get. I mean, if it's a very hard source, you will see like very high ionization lines. If there might be outflow information, we might get. The one we are seeing is H alpha, so that gives us a star formation indication. So each emission line, or sometimes if there is absorption line, gives particular information of that object. So this we can say, since it's showing the H alpha line, so we can say this might be a star forming galaxy. It's a galaxy.
If the line was broad, then there'd be an AGN.
Yes, AGN also. Yeah, AGN also is possible. So based on like after fitting. So now what we did is the initial thing. Like I told, right, we just want to see like after getting, you can like plot and do fitting and all, and see if it's broad, how it is, and based on the emission lines, you can do what like Saili showed that there are BPT plot or band plot. You can distinguish what kind of source they are. Now Saili will show MUSE and MaNGA, which are like IFU data.
So any other question?
It was a MUSE data, but she will show like other analysis.
Others will be there as well, but if you want to see just the high ionization photos.
You can go, I mean, you can check each wavelength, like each what kind of emission you have. I just showed because it was like maximum at that point.
Like you have said about the power lines, so optical, if you want to the star, if you want to see in the UV lines, that is a.
Okay, so Amrita gave us the introduction about the cube data. So here this is the cube. You can see there are many grids and it has 3 axes. So here the Z axis is basically wavelength information. She already showed how the cube looks in PS9. And X and Y axis is basically pixel information, basically RA and DAGN that we call. So yeah, so cube has 3-dimensional information. Okay. So MPDF is one of the tools to handle cube data in a scientific way. PS9 you can use just to visualize and understand the thing, but to do science you need to do like with corresponding error and everything estimation. So you need to have a better estimates. So MPDF is one of such tools. So I have shared the installation and everything. So you can try it later on, and because we don't have that much time to go through any issues we are facing. So what it does, so you import several libraries. So here I am importing cube, something called cube, which basically reads the cube data, and anything you can handle, like anything you want to do with the cube data that you can do. So I am reading here the same cube that Amrita showed, ngc 40.fits. So the cube is stored in this in this location of my system, and when I'm reading the cube info, it is giving me the information of the cube. Like if you see the first line is saying, obviously zoom in a bit, we can't see very well. It is, yeah. Yeah. So when I'm so when I am in like reading out information, it is giving me the info three dimension. 3682 is the wavelength. 30 by 30 is the pixel frame size of the image. So it has basically 30 by 30 image of 360 like 3682. So you will get 3682 image if you like get a single slice for the cube. And like the center of the galaxy, what is the like size in corresponding arc second? So for MUSE, each pixel size is 0.2 arc second. So you are getting like what is the size of this 30 by 30 pixel frame. And what is the corresponding minimum wavelength and maximum wavelength? So it covers mostly the optical range, 4750 to 9350 angstrom. And what is the wavelength? Is 1.25 angstrom. So each 1.25 angstrom data, you will get one more image. There is an interval between two frames in wavelength dimension is 1.25 angstrom. And then when you read the header, so in header it contains all the information about the observation taken, like taken observations, with the PI, when the observation is taken, what is the sky conditions, everything will be given in the header information. I'm not going into that detail. And data, when you read the data, it will give you for entire 30 by 30 frame size data, what is the pixel value at each point for entire 3682 wavelength dimensions. We'll get the data like values for entire cube if you read the data. Like what is the unit? So it's an optical data, so its unit is in flux density, so ounce per angstrom per centimeter square per second. So this is the unit of this in terms of 10 to the power minus 20. So for each pixel, whatever flux value that you are getting, you have to multiply with 10 to the power minus 20, then you will get it the flux density conversion. With the, let's say for the count you are getting, and if you multiply with like 1 is your count that you are getting for each pixel, and if you multiply with 10 to the power minus 20, then you will get into a flux density dimension. So then it will be converted into this unit. And what is the data type? It's a float type data. Similarly, now you have stored your data into Q variable. When you read Q 000, it will give you the information of the 0th wavelength frame, that is 4750 angstrom, 0th X and 0th Y position, means first pixel information in the bottom left, like X0, Y0. This is the corresponding flux value at this like 0th first wavelength, 4750 angstrom, and 0th is 0th position. And similarly, you can read, let's say, for example, any other wavelength range, any other positions. I am just giving two examples, extreme example. This is the first pixel, and this is the end pixel, that is 29, that is 30 pixel. 30 pixel is the box size. The last pixel is 29, and the last wavelength is 3681. That is the wavelength frame. Corresponding wavelength is 9350 angstrom. What is the corresponding pixel value? Now, what happens if you like collapse the image, collapse the cube with respect to z-axis, means wavelength axis, means you are collapsing all the wavelength. So then you will get only one image. So now what happens? You have image at each wavelength. Now you summed up, completely collapse it together, basically taking a sum. Then you are getting a single image, which is now called as a white light image, because entire wavelength range information you are getting in a single frame. So this is what is happening. We are collapsing or basically taking the sum of axis 0, that is the wavelength axis, and what we are getting is the white light image. Similarly, you can extract the image for single slice, like single wavelength information. So I am extracting here the image for 1451 frame size, which is corresponding to 6000 angstrom wavelength. So here it is basically some like something called H alpha H 6500. Single slice also you can basically get just by giving the slice number and entire like X and Y you are reading entire experiment. That's why you're getting the image frame here. It's a single image, single slice. Okay, so when we basically sum.
So here you've given the whole 30 by 30, which means if I define the X, I can get a crop version.
Yes, if you define like here, if you give the like X and Y range, you will get a crop version of the image. Similarly, you can define the cube range, like the slice. Instead of 1451 giving it a single one, you can define the range and you can crop the cube as well. You can get a cropped cube in the wavelength range. Yeah, so when we sum the 0th axis, basically wavelength, we got an image. Now, what happens if you sum first like X and Y axis? Basically, you are summing entire image pixel informations. That means you are only getting the wavelength information. So then you are getting the spectra. So when you are summing up X and Y informations for entire like galaxy or entire frame, you are getting a single flux value for each wavelength. So if you are getting basically a spectra. So this is the spectra for the entire image that's been shown here. So basically sum for each pixel for the entire X and Y dimension, and then you are getting your corresponding spectra. Now this is the spectra. Then you can basically, let's say for example, you want the information for this particular emission line. So you can basically take an integration over that region and you will get the corresponding flux value. So it's a unit in the unit of 10 to the power minus 20. So you have to multiply with the corresponding like value with the 10 to the power minus 20 factor. So it will be the flux density. What else you can do? In the galaxy, you can define a central, like you can define a region. Let's say, for example, here in the previous years, I entirely taken the sum of the entire X and Y axis and got one single spectrum. But your science might not require that. You just need a simple, a small region information. Then you can just define a small region. What I am doing here, I have defined the central region in terms of RA and X. This is the day, this is the RA. So here, X-axis is declination, Y-axis is RA. Always remember it's opposite. In image, we think X-axis is right assumption, Y-axis is declination. But in cube, for example, MUSE cube, X-axis is declination, Y-axis is your RA. So you're giving the center information and you want a 2 arc-second region information in terms of spectrum. So I am like basically extracting an aperture at the center, given a center like 2 arc-second region, and extracting that region spectrally, not the entire cube spectrum. And then I am fitting a like normal polynomial, because you can see there are lots of absorption informations are also there. Just to remove that, I am fitting a polynomial and then subtext. So this is your residual, and this is the spectra, and the corresponding polynomial is shown here by a curved line.
So you can do it for every spectral.
You can do it for every spectral also. Here I am doing for a region of 2 arc-second around the given center. So I am defining this fixed. This is in RA tape. So I have defined this RA tape and I have drawn a circle. So then I have summed everything in like every pixel's information for each plane, basically each wavelength, and then getting like one flux value for each wavelength within that circle. It's a sum value. SP dot integrate was within this wavelength range.
This is the center of the circle.
No, this is the entire cube. So here I have just taken the sum of 1, 2, means entire x-axis and y-axis. So this is one value for entire cube. Second line is I am defining a. So this is the integration. So what I am doing in the first case, I have summed over the entire cube and I have plotted one spectrum. Now I want the integrated flux value within certain wavelength range. So SP dot integrate does that. Wavelength range, yeah. SP, whenever SP comes, is for the spectrum. Whenever image or cube comes, it's for the image. So that's how it's like spectra is defined as the SP.
Next one, that 1 arc radius around the center. This is who is the diameter 1 and
Who is the radius?
1
No, it is this is not arc second, this is in pixels. So 2 pixel is corresponding to 0.4 arc second in the means for the mean data. 1 pixel is 0.2 arc. In the means. I think I said it. Yes. Yeah, you. Oh, SP dot integrate is giving the range. So in which wavelength range you want to get the corresponding integrated flux. So range is like x this to this. So it defines like x1 to x2.
So after you run the code, you can go back.
Oh, okay. So what is happening? Oh yeah, right. What is happening? I think it is giving me two fluxes value, but those values are completely different. One is very large. Now I'll check why there are two outputs. Like whether it is doing within that interval range or doing at two different points, basically, given point. I'll just change it to one wavelength and yeah. So next, this is the like yeah. So this is for the central region. I have drawn the spectra, and then what you can do, if you see here, last line continuum subtracted range. So what I am doing now, I am plotting the spectra within a zoomed in version, zoomed in range. So I'm not plotting the spectra within the entire. So in the first image, the spectra has been plotted from 4,700 to 9,300. Now I just have zoomed in and plotted the spectra only for the 6,500 to 6,850. Because I want the information of certain lines, certain emission lines. I know like based upon the redshift of the galaxy where the H alpha or N2 or O2 lines will be, redshifted lines will be. So I am just zooming into that region and getting the information, like to look into the line information. Now what you can do, you can fit the Gaussian profiles over those lines. So here I am fitting the like Gaussian profiles over these three lines, N2, N21, N22 and H alpha. So N2 is a doublet line around H alpha. And then I am just plotting the zoomed in spectra with the Gaussian fitted lines. So once you fit the Gaussian lines and plot the like ask it to print the parameters, it will give you the Gaussian center, Gaussian integrated flux, Gaussian peak value, FW and continuum. So all the information you will get from the Gaussian fitting for the particular line. You can basically extract for each line's information for a certain region. So this method we use generally to get the if the galaxy is there and we don't know its redshift. So we just fit the corresponding Gaussian line and we got the corresponding Gaussian center and use this wavelength to estimate the redshift. So we know there are three lines which will be adjacent always if the galaxy is a star forming or having N2 emissions. So you know like these three lines will be adjacent and this is like signatures of the three lines that will be appearing. So from this three line modeling, you will get the corresponding wavelength, and then if you use those wavelength, it's very lambda 1 minus lambda 2 kind of information to get the shift in the wavelength and the observed wavelength and the delivered rest frame wavelength, and that use that information to get the redshift. So if the galaxy is having unknown redshift, you can use such information to get the redshift of the galaxy. Next, I'm coming back to the information. So this is the tube data. If you want, for example, when we work in imaging, we use R band data, V band data, I band data, different optical and infrared band data, for example. So you can simply convolve those corresponding bands. This is, for example, Johnson V band, cousins R band, cousins I band. So you can simply convolve and get corresponding band images as well. So it has the information of the response curve of the corresponding band. So once you know the which band you whatever band you are defining, it will basically give you the corresponding band image from the tube data that you are fitting in. So here I have just shown three band images how you can create it. Now last thing that I will show is the H alpha emission line image. So when we create an emission line image, most important thing is to subtract the continuum. So if the recipe is same, I am taking a zoomed in version because from the earlier plot, I know where the H alpha line is residing. So I am just creating a zoomed in version of that and plotting here the zoomed in version of the spectra. So this is N21, H alpha and N22. So these are the three lines. But when you want to get the H alpha information, so this is for a single pixel actually. So once you want to the H alpha information and you have to subtract the continuum, there are two other lines that are there. So once you if you want to model it, this contribution from these two lines will also be appearing. So what you have to do, you have to create a mask. This will from for example here to here, just to remove the emission lines and then fit the continuum to get the continuum information. So in the second case, what we are doing, I have created a mask in this region where the emission lines are appearing, and then fitted a single polynomial. You can anyway check if the multiple approaches and take like chi-square minimization kind of technique you can apply, whether your fitting is proper or not. And just for simplicity, I'm just doing a single polynomial fit. Then I have unmasked it from the fit, like from the spectrum, I am subtracting the continuum and then plotting the line fit. So this is my continuum subtracted lines. Same thing I will repeat for each pixel. Same thing I have repeated for the each pixel of the cube, which is being done here in the loop. And then at the end, I'll get a continuum subtracted H alpha map. So once I have done for a single pixel, same thing I have repeated for the entire like cube within that range of the H alpha, and then I am finally getting a continuum subtracted H alpha image for the galaxy. So I'll stop here. There are any questions? Option over these NPDEF. We can convert this. Taking care of the so from the emission image, you can't convert a velocity kind of map. You can't do that. Simply you can just using like velocity relations, like wavelength to velocity relations, that you can do, but they don't have any function which will give you the velocity map, like rotation distance. That you can't get. But a systematic thing you can get from the redshift information. Yeah, that will be a systematic like velocity that you will get. But if you want to subtract the systematic velocity and get the rotation velocity, that this thing can't be able to. And another thing is, I have to take care of this. There will be some way like I want the slice of the for HL slice. That can be done. I have shown one. So this is kind of HL for slice only. Like this is continuum subtracted HL. For other things. You can create a mini cube as well. So I have shown there somewhere. Yeah, so this part. So if you want to create a mini cube, you can, this is the wavelength information. You can give the wavelength information, let's say colon, what range you want. And this is the X and Y entire image range here. Then you can save this thing as a cube, subcube basically, for a smaller wavelength range. Are there any other questions? Anyone? Okay, so I'll hand it over to Chandan now. Yeah.
Yeah. So this section is for a MaNGA. So MaNGA is a mapping of nearby galaxies survey. Okay. So whatever Saili is presented, that was using a MUSE data, and she has used a tool MPDEF. So what I am using, that is a marking tool, which is specifically designed for a MaNGA data only, and it is very simple tool. You just know how to use that, and all the outcomes are very easy. I will just show you. So I hope everyone has that file or not. Yeah? Yes. Everyone has this file, yes or no?
Is it also file?
Yes. Okay. So I'm going to talk about this plate ID. So this is the MaNGA one ID, like in the STS they have a plate ID. So whatever the galaxy. So whatever the galaxy they observe, they have an associated one plate ID, you get related to that IFU. So the one I am going to talk about, that is 84816103. So you can see the image of this galaxy. So in the MaNGA, sorry, marking, if you want to display a STSS image, you have to just write this function called marvin.tools.image import image. You have to just write the plate IFU there. It will automatically show what is the image associated with that galaxy and with its field of view. That magenta color, it's a field of view of the MaNGA, which is different for a different fiber. So MaNGA has a 5 fibers actually. So for each fiber, they have a different field of view. And you can see that there are two galaxies there, which have two different nuclei. This is, I choose this galaxy because of this constant, the galaxy merger, two galaxies are merging with each other. You can see it here. So what we can do that if you want to see quickly, what is that galaxy, whether what is happening to that galaxy. So like I told before, first thing we can check the signatures like H alpha, if whether there is any star forming signature. Other is whether it's a hosted high ionization like O3 signatures. So what I will do, so from that, before that, let's know what you can do with the marking. So just you have to first you have to invoke the maps with their plate IFU, and then there's a data model. Within data model, you can see whether you want to in that pixel, whether you want the directly flux whatever is coming from that, or you want to fit a Gaussian, and then you want a flux. So there's a different like spexels, twice flux is also there. That the different lines are also there. So yes, you can see that. So this is a emission line S flux, which is a emission line with their spectral flux, like whatever is coming from the spexel, directly whatever the flux is there. For each line, like it's a O3 lines, H2 lines, H beta lines, whatever line you are interested in. And also it will give you the G flux, emission line G flux. Like they will fit the spectra with a Gaussian and see whatever the flux is coming from. So to get rid of the noise. So how it works? So this is the map. This is H alpha map and this is the O3 map. So this is the image. You can see two nuclei are there, right? So now we want to see which galaxy has associated the star formation and which has a high ionization like O3 or so. So first we will see the H alpha map. You can see that this is that nuclei which is at the center, which has a H alpha emission, but the other nuclei does not have a H alpha emission that much of prominent. But in the O3 map, it is more prominent. So if you want to see the signature, these lines are very useful. Like what is happening to the galaxy and how the interaction is going. Okay, so you can compare this with these maps and see like visually what is happening to the galaxy. What is the arms are have a star forming and the nuclei are whether it's a O3 emission is there. You can check other emission also H beta, O3, N2, whatever you are interested in. Other thing we can also check the what is the velocity associated with it. Like it's a H alpha. It's a Gaussian H alpha velocity, like how the gas is moving within a galaxy. So this is an interacting galaxy. You will not see the exact blue shifted or red shifted rotation within the galaxy. So that's why it's a like mixing is there. So it's not properly visible even in the stellar as well as in the gas. But you can see the how the gas or the stars are moving within a galaxy using this flow. So it's very easy. You have to just write here maps to emission and G velocity. It will give you the velocity line emission map and also the stellar velocity field. It will easily you can just plot the flux as well as the velocity depending on your size, what you want to do. Other thing, if you want to check, like now we have a two nuclei within this galaxy, and we want to see what are these nuclei, whether they are star forming or they are AGN or within AGN, two categories are there, CFAT or a liner. CFATs are very high ionized and the liners are low ionization. And we want to see, so in a marking, you have to just write maps for get BPT. So BPT is a line ratio map where you can, it will tell you what is the nuclei of that galaxy. So here I have used two BPTs and it will give you this kind of map. So you can see the red color is a CFAT and the pink color is a liner and the nuclei which is at the edge, it is a AGN which is a CFAT and the nuclei which is at the center is a liner. So you can easily get the information what is the nuclei there, whether it's a AGN or not. So this is very important in case of when you want to see whether what is happening to the galaxy, whether the two AGNs are interacting with each other or when the AGN the other is just a star. And up to that one, any question? Other than marking, what you can do that we have a one galaxy and we want to see what has been observed for this galaxy. So that is called value-added catalog that Marvin has already provided. So MaNGA has already provided. These are called value-added catalog, and we want to see these galaxies very other which catalogs. So you have to just import this VAX, which is value-added catalogs, and you have to just write like you have to import the cube and just type cube.vac. Then it will give you whatever the available catalog. This galaxy is available in the available catalog, which has MaNGA has already processed. So Firefly, Galaxy Zoo, GZ3D, M and H1. So I will just show one or two of them. First is Galaxies. So Galaxies is that it is a citizen science project where people, like any layman, normal people, they can go to the screen and just see what is the properties of the galaxy, whether it's a spiral galaxy or elliptical galaxy or whatever the signatures are there. So if you just want to see what about that galaxy, you have to just write wax.galaxies. It will give this to all the like properties available in that catalog of that galaxy. Like let me show you the some of them. So what is the morphology of that galaxy? So it's classified as SP, question mark, and R is a ring. They are thinking that the ring galaxy is there. SP is a spiral type of galaxy with the Hubble classification. Other thing you can say, what is the morphology class? So it's a whether what is the kind of like whether it's a disk galaxy, how much its probability, it's a 69% chances that it's a disk galaxy. Other is whether it hosts a bar or not. We know that from the visualization it does not host a bar, and you can see it's a 3%. So it means that does not host a bar. Other is whether it's a spiral galaxy or not. You can see it shows that 21% chances that it's a spiral galaxy. Other is whether it's a merger or not. So it shows that 64% chances that it's a galaxy which is undergoing a merger. What else? Other catalog is the H1 catalog. So you can see what properties are available in this catalog. So these are the following properties. I've just listed a few of them. One is what is the stellar mass they are using that H1 data, and what is the log H1 mass limit. Like they have in a radio, they use a velocity width of 200 kilometers per second. That's a associated mass later with that. So there are various properties are there that you can extract using this catalog. You don't need to do it by your own. You have to just go to that catalog and just extract it. Other is a NSA catalog. NSA is a NASA Sloan Atlas catalog. So it has already observed 2 lakh or some galaxies where the properties are listed. What is its ellipticity? What is its position angle? Or what is the searching index of those galaxies? Searching profile, like within that searching, like how much of the flux is there. So you can easily check what parameters are there. And the redshift, spectroscopic redshift also. And what other properties are there. So I listed some of them. So let's suppose it's a redshift. What is the redshift of that galaxy? It's a 0.046. And what is the stellar mass? 10.598. And what is the half-light radius? Like a half-light radius is 50% of the flux where the and so this is the half-light radius. And then the axis rays. So they fit the galaxy with the elliptical contours, and they whatever the lowest surface brightness contour is there, they see what is the associated B and A, semi-major by semi-minor axis ratio. And then the magnitude also you can check. So they have listed out the magnitude: FUV, NUV, U band, G band, R band, I band, and Z band. So all of the band magnitudes are also available. You just know how to use this tool, and you can extract lots of information from it. That's it. So any questions if you have? Does anyone have any questions?
You do the part where you try to find the galaxy of the number. Number one and find that.
Which one?
So starting is talk about the plate ID. To find the plate ID for a particular galaxy from the website or vice versa.
Yeah. So I just checked the literature where people have studied some of the merger galaxies. I just took that galaxy for this set.
So if one was to search for their galaxy of interest, how would one go about that?
So there's other things are there. Let's go. You can go to legacy survey. You should know the name of the galaxy. You can just put it here.
We also have a question.
So let's go. This is the same galaxy. So this is a legacy survey. for the legacy survey. So they have listed all the species, Bulges as well as for what galaxy the MaNGA data is available. So this is the galaxy. So I went to the legacy survey and checked some of the merger galaxies. And then I could then check whether this galaxy was MaNGA data. So if you just load that, it will show that it's hexagonal type. So if it doesn't tell MaNGA data, so you can work on that. So apart from that, there is one more thing called margin web. So if you don't want to go to that Python or Excel, so you have to just write the plate ID here. Then just press enter, and it will give you all maps available for this case. Yeah. So it's an interactive video.
So for what spaxel, can you explain what spaxel is, unit, and how do you find out?
So how do you find it? So you know about the image, right? So it has X and Y. So whatever we divide the image into pixels, like in a CC. So that particular rectangle we call a pixel. But in a cube, that pixel is extended up to a wavelength. It's a third axis, which is called wavelength. So that we call a specs. Yeah, but just extended.
Not just one small quantities.
Spaxel is whatever you call a pixel in 2D, spaxel is a 3D.
Yeah.
Yeah. Entire wave. For one particular level, you can have pixel, but for the 3D, you can place specs.
How do you find out the size is arc second from the header, right? It's the header.
So for each, we already know, like for MUSE, that it's a 0.2 arc second. For MaNGA, it's 0.5 arc second. So we already know for each instrument what is its size, pixel size, what area of sky comes.
Even given the header also.
It's not loading.
Wi-Fi is giving up.
So, but margin that you can do the similar things, but you do it on a Python one. That's you don't have any questions.
Yeah,
let's end this session. And it's 5:30. So we have a dinner at 7 o'clock at the same place, ICNAM. Okay.
Well, you all come for dinner, okay? Everybody, 7 o'clock, tap up. And you can just break and take a walk or just relax.
Yeah, how you can explore it.
Okay. Let's just go to what happens.
चले